or sooner. We're live. Okay. Helps if I turn. There we go. Microphone on. All right, guys. Day 3. Look at that. So, in other words, you guys are now over the halfway margin. How's everyone doing?
My brain's fried. Hi, morning things that I never in a million years thought I would need to know.
I like that one. We came back. That's perfect. All right. So sorry I missed last week. I was on my honeymoon, and also it was my birthday on the same day. So the 2 reasons why I wasn't going to be here. So, all right. Let's get on here for the homework. Did anyone bring your antenna designs with you?
I forgot.
You forgot?
Until I got in the car.
Okay. All right. Not a problem. We have every example of the common antennas you will use here. So we'll go through that in chapter 7, which is the antennas chapter, as the first thing we'll start with. So the big thing we do with the homework is to get from unprepared to prepared. That's how we're going to get you guys to pass the test. So our outline today, again, you're already over halfway done with this course. We're going to go through chapters 7, 8, and 9 today, and then next week we get to finish the book. Yes. And then after that, we'll go into a testing session. Again, the process to success is keep repeating what we've talked about before. Read the chapters, go through the practice test, get any questions you have answered here in class, or you can email us, and we're making sure that we get this. Also, rewatch the classroom sessions on YouTube. If anyone needs those, let me know because they're hidden. Okay. Remind me of the email address, and I'll get you all 3 that we've done, including today's, so you can rewatch all of those. We got to watch you guys last week from Grand Junction for about an hour before we finally said, let's go to dinner. All right, so.
That says a lot about it.
I was just going to make
I know this crap going to dinner.
Yeah. Okay, so last week we were supposed to do signal propagation example. The instructors kind of forgot about it. Do we need to go over with it with an example? We'll show how signal propagation really works with the antennas. Might help some people with the propagation, or are we good in here?
I think we covered that with the diagrams of the wall.
We all good? Okay. All right, so with that, we'll keep going. Like I said, we're going to do chapter 7 through 9. So 7 is antennas, which is like the coolest chapter of the entire book. Then we're going to get into some more mind-numbing with It's Electric and Hamtronics. Don't worry, when you read the head of the book, did everyone read ahead? Okay, so a lot of that's still confusing, right? Kind of. Yeah.
Chapter 9 got that way.
Chapter 9 definitely gets that way. I'll tell you what, as soon as you leave here today, all of those are going to click. You're going to, oh, I get this now, we're good to go. So.
Okay, we're holding you to it.
All right.
That's a satisfaction guarantee.
I'm gonna watch you guys at that moment when all that light turns on. It's like, oh. And I'll see everyone do it. And then we're hoping to be out again by 9 o'clock. I heard last week you guys got out pretty early. So
We were right on time.
you were right on time?
We were right on
Yes,
time.
we were.
I saw you guys got out early. All right, are there any questions before we begin today? I know we did a little kind of pre-talk before our class started. One in the back.
I just had a question on some of the definitions. They don't, obviously from experience, there's certain words I know, but they're used in a different way.
Mm-hmm.
Whether it's inductive or, whatever it is. But there's some things I just can't understand, like the word resonance. What is it?
All I can think of is something bouncing
Well,
like
I know,
this.
that's, in my mind, that's what I'm thinking.
It's vibration.
It's
Okay,
vibration.
it is vibration.
Once we get to the antenna chapter,
Yeah.
then let's see
Okay,
if we
well,
can
that's
still
what-
have that.
Yeah. Okay.
Yep.
Any other questions we want to touch on? Resonance is a really good one we'll work on today. Any others? Okay. Let's go ahead and jump right in. And
And that's resonance.
Resonating with his little brain.
Yeah.
So we'll start with chapter 7 today, which is antennas. And we're going to go ahead and turn this over to Dad.
Okay, so we're going to talk about some common antennas, calculate the antenna length, difference about mobile antennas, and what's the dummy load. Antennas, I think, are the most fun part about radio is antennas, because there's so many things that you can do with it. With the radio, you're kind of limited, unless you're really build your own radio, field tubes, and all the resistors and stuff like that. That gets to be really overwhelming sometimes. Making your own antenna is a lot of fun. One thing about radio that you have to understand, it's like any other hobby you get into or any other science that you get into. There's something that's that cornerstone, that one element that's a cornerstone. Antennas are that cornerstone. You can buy a $7,000 radio and have a cheap piece of crap antenna and not have very much fun with it. Or you can really put some good science and workmanship into an antenna and have a $70 radio and outperform that $7,000 radio. I know this because I do it. I have a radio that is vintage 1950 something or other, and it outperforms the $7,000 top of the line Kenwood radio that my dad has sitting right next to it, because our antenna is that good. Really put some time, effort, and concentration in science into building that antenna. You notice I didn't say money in the antenna. You can build antennas really cheap and outperform some of the most expensive stuff. It's just understanding what makes a good antenna. So we're going to talk a lot about this, and I really hammer on antennas, not only because it's stuff that you need to know for the test, but it's great stuff to know when you're operating a radio. There's more times than not, I've talked to another ham, and they're having some issue with contacts, and I start asking questions about the antenna. Oh, I bought this antenna, it's fine. Okay, well, did you check this? Did you check this? Did you check this? And finally, they go out to their antenna, swallow their pride a little bit, go out to their antenna, and they find a loose connection, or they find something has broke on their antenna or something. And it's just some little tiny thing screws up the whole deal. So simple things that make a complicated problem. So antennas are really important to us in radio, and understanding the antennas is really important. What?
Nothing.
Okay. Some terminology. A half-wave dipole is your most basic antenna. So we have two conductive parts of equal length and a feed line connected in the middle. So we have one part of conductive length, the other part of the conductive length, and our feed point. Usually this is a coax, which is that single cable. You've got a conductor in the center of it, you've got an insulator, and then you have a shield around that, and then you have a protective coating on the coax. Sometimes you have what we call a ladder line, where you have two conductors, and they are there's little strips of plastic that go across in the middle of it. It keeps the two conductors apart from each other. We call that a ladder line. Or solid in the middle, which is just a feeder element. Remember back longer than I care to say that it was, the antenna wire that we used to have coming in from those antennas, TV antennas that were on the roof, that flat wire that came in, you have a copper wire on each side of it, and plastic in the middle. That's what we're talking about, a feed line. Okay? There are designs of antenna where we're actually using that feed line as part of the antenna. In place of that, the antenna won't work. And I'll talk about that later. So again, it all depends on the materials that you're using and how we balance our antenna. We want to balance our antenna to make sure that both these halves are exactly the same. And if we're using this feed line as part of the antenna, we have to use this in our calculations also. So there's a lot of math that goes into this, a lot of science. Once you have that aha moment, you'll be like, this is really cool. And I have a lot of fun making antennas and stuff. A lot of the antennas that we have here, I've made some of these myself, and the others the dipole. So we made a lot of these ourselves, and little to no materials that it cost us to get into this. So, what are we talking about here? My antenna. So this is a coax. Again, this is that center conductor, and it has an outside shield. So we're not using the feed line as part of the antenna. We're just using the radios. We call this a dipole antenna. What a dipole antenna does, this dipole right here, this is suspended in air. Then our coax is connected into the center. Yes. She has a question or a thought. It was the light bulb over. I saw it. It's all over the room.
The coax is never part of the receiving or transmitting.
Right. All it's doing is taking that signal from my dipole and putting it into that coax and sending it out on my radio. There's our designs that has that feed line. It's not made out of a coax, it's made out of that wire. That comes out of the ring mat.
But the transmitting and receiving part probably has copper.
It is copper. So that's the stuff that we have. Now, you can use aluminum, you can use steel. I have aluminum electric fence wire on my dipole in my house that each section is 52 feet long. So it's 110 foot long in fence. But it's aluminum electric fence wire. Why? Because it was cheap. And I didn't want to come up with 110 foot of copper wire because at the time copper was incredibly expensive. It was like $3 a foot. And I didn't really feel like putting that expensive. For $3, I bought 500 feet of aluminum fence wire and with my antenna. And I've been talking around the world on it. So those are the different materials that we have. So what you have, as the signal comes out of the coax, comes up into this balun, this is what this is called a balun, this balances out our antenna. We'll talk more about that in a minute. The signal radiates out in the 360-degree circumference from this antenna, okay? So as this is horizontally polarized, remember that from last week, our signal's going out this way 360 degrees. So part of the signal goes down to the ground, part of the signal goes up straight up in the sky, and some of it goes out to the side. Okay, so it makes this donut around that dipole wire. Does this make sense? Okay. Simple dipole most often mounted parallel to the Earth's surface, so horizontally polarized, which is what I just said. These are two test questions. Your free space is the half-wave dipole radiates strongest broadcast to the antenna. Our free spaces are out here in the air. Very simple connection. You just have your center connection goes to one side. Doesn't matter which side, left or right, doesn't matter. And your outer shield goes to the other side. And again, it doesn't matter as long as it's the opposite side. You can't put them both on the same side. Won't work at all.
Okay, go back.
Okay. Maybe. There we go.
The outer braid and inner conductor. So I get on a coax, your conductor is the center of the Tootsie Roll, basically.
Correct.
So what's the outer braid? That's the shielding?
That's a shielding. Yeah.
Okay. So is one acting like a ground, so to speak?
Right. The outer shielding is your ground, and the inner conductor is your transmitting signal. What this does when you're transmitting, this balances out. So the RF hits this, and because of this wire that's your shield or your ground, it balances it. If this is a 40-foot wire and this is a 20-foot wire, your signal is out of balance in your SWR. You guys read about SWR? SWR goes crazy. You'll get a 3.0 or higher, or infinity is what we call it, on your SWR because the antenna is out of balance. So these lengths, whatever your calculation says your length has to be for that frequency you're transmitting on, they have to be in balance.
And when you say your antenna's out of balance, what are you seeing? Are you not getting signal out? Is it static?
You'll get signal out, but you get a high reflected signal that comes back to your radio. That's what a high SWR does. If you have a high SWR, you'll have a high return signal that comes back to your radio, and you'll burn your radio up. Literally, smoke coming from the radio burn your radio up.
How
So,
many
very important.
wires are inside that coax?
Two. Conductor and your outer shield.
The
specific direction when compared to the reference of the antenna. So my gain, how much gain do I have for my antenna? The Yagi has the gain going this way because that's where the antenna is pointing. There's less gain on the back than there is on the front because all my signal goes to the front. So that's where my higher gain of the antenna is. Make sense? We're back. Yagi antennas. Again, there's my driven element. That's where the signal goes in. That's where the coax gets connected. There's my reflector. And this is my director. So my signal's produced from here, goes out 360 degrees around that element, goes out, hits this reflector, goes into the director, and the director continues on. Now you do get, like VHF antennas, I have one of these things. There's 12 of these. And they're the same size as they go out, and it laserfies. It makes that signal more of a laser pointer. It's a good and bad thing. I can make it more precise on where I'm going with that signal, but that's bad too, because if I'm off just a couple degrees, it's a couple miles, down range. So they're more finicky, if you will. But for really low signals that I'm trying to pick up, they're great. You just have to have more patience to dial them in to find your signal. So the longer that is, the more precise you can be on finding that signal. But they can also be a little more finicky. So rubber duck comes standard with the handheld. We said those aren't really good antennas. They're really poor quality. It's called a BNC or SMA. This is an industry label. I don't know what those letters stand for. Never been told. Just understand they're called. Connector or an SMA. Do you have a BNC on one of yours? Because this is an S. On the mag mount? Oh, on the cable itself? Okay. SMA, BNC. Just industry standard. So when you go to an antenna store or you go to the radio store, anybody go to one of the radio stores we talked about last week? Nobody went to the candy store? Okay. Because they'll ask you, they'll ask you what type of connectors on your antenna. Is it a BNC or an SMA? And you can speak the lingo. That's what they're asking you. Okay. Compact and convenient. I'm sorry? No, they're not. You can buy adapters, but every adapter that you put in line reduces the performance of your antenna. It risks a loose connection and it reduces the performance of your antenna. So the fewer connectors that you have between your antenna wire and your radio, the better performance that you'll have. Okay, so yeah, the rubber duck, poor performance. The longer antenna, closer to half wave that you can get for a handheld, the better. That's why that antenna is so much better than this antenna. Half wave, quarter wave. Okay? Yep, sure is. Yep. If you took that outer covering off, you'd see the wire coiled up. It's like a spring. That's why it floppies. Okay, so that mag mount antenna that you have, those are best for car antennas because it's compact, goes on a mag mount, much better than a rubber duck. Your directional antenna, which is that one, boy, it looks like the same antenna, doesn't it? Very popular antenna, by the way, especially for guys. This thing collapses, that orange tube, that whole antenna tears down and goes into that orange tube. And the elements that he has inside that orange tube is the UHF side. That's actually a dual band antenna. I can put UHF frequencies or VHF frequencies through that antenna. It's just the way it's designed. And like here, he only has the VHF elements installed. I only have the VHF on that one. But you can do both at the same time. Won't hurt it at all. So what's the difference about mobile antennas? Oh, okay.
Emergency band. The national call frequency. National call frequency on 2 meters is 146.520. It's not an emergency frequency. That's just the national call frequency. Yeah. Or you could use a half wave. Yeah, it depends on the radio that you're using. A quarter wave is a smaller, more like this, than the half wave, which is a longer antenna. Yeah, half wave is better because you signal. Longer is better. Yeah. I know. We'll get to that in a second.
The way I remember the half and quarter, how to tell which is better, just remember you've got a wave going out there, a half wave is catching half the wave, and a quarter wave is only catching a quarter of the wave. So you're getting more with that half wave.
More performance. Okay, so what's the difference about mobile antennas? They're on cars. Makes it pretty simple. Mobile antennas are often mounted in the center of the vehicle because that normally provides the most uniform radiation pattern. That car is your reflector, that's your ground plane, so it's taking that signal that's coming off of the antenna that's mounted on the roof of my car. The signal hits the metal of my car and bounces off. If I have it off to the side, more signal will go this way because I have a better ground plane than off of this side. Or on the other side, more signal will go this way than on this side. So if you have it in the center, it goes out more evenly from the car. Make sense? Right. No. 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 And it, right. 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 It's he's kind of made a weird Yagi out of it because wherever the front end of the car is pointing, that's where most of his signal's going. So when you're driving down the road, I hear you really good, not so much anymore. Okay, I hear you really good. So it makes it kind of funky that way. So to his point, the more center you can get, the better all around transmissions that you're going to get and performance is what I'm trying to say that you're going to get. Okay. So we really screwed you up with half wave and quarter wave. Now we have a 5/8 wave VHF or antenna. Offers lower angle of radiation. In other words, it doesn't go out as far, it doesn't go out as high, and more gain than a quarter wave antenna, usually providing improved coverage. So the longer the antenna, the better. The more angle of radiation that you can get, the better. 5/8 is at more or less than a half wave. More. It's a longer antenna. Okay? I don't know. That's the way they wrote it. That's the way they wrote it. Because this is a test question, and you got to ask those guys who wrote the test question. Yeah, it's kind of like the math gods. I don't have a good answer for that. Yeah. But you got to break it. You got to break these things down into because they say a half wave and all this down to a quarter wave. We focus in on the half wave right away. I was going to sit there and think it's 5/8 more or less than a half. Oh, it's more than a half. Okay, so that's longer. Well, that's better because yeah, it's going to be better than a quarter wave. Right. Angle of radiation is how the signal out from the antenna, because this is your ground plane. The shorter antenna, it has shorter distance to travel. Right, distance to travel, so it has a shorter angle. The longer, I've got a bigger wave, I get wider takeoff from it. It goes further. Exactly. Yep. There. Type of loading. Yeah. That's why it works better. The higher up you go, it works better. Right in a hot air balloon, and you can take a quarter wave antenna, you can talk to Denver. Pretty neat because there's nothing between you. There you go. There's a lot of the balloon folks are on ham radio, so because they can talk a long ways, so it's kind of cool. Okay, so the type of loading refers to inserting an inductor in the radiating portion of the antenna to make it electronically longer. This is the load. I've been talking about this the whole time. This is the load. So in Chris's antenna, this black base right here where my hand is, this is a load. This is a load. Thank you for clarifying that. Yes. So this is the load, and this is a trap. The coil of wire, this is a coil of wire too, to make it seem longer, but they call this a trap. Right, because for VHF, it's using all of this, so it's only trapping the signal for UHF to prevent this from being seen as a UHF. This is seen as a UHF. This is seen as VHF. The dual band antenna, yep. And this is the load to make the radio think that this is longer and this is longer. So this is a high gain antenna. You can get a lot of good distance out of this antenna. Yeah. Well, they're multibands, but that trap does that. That's why there was two. There was a trap here. There's a couple inches, and then there was another trap. Yeah, that's telling me how many different bands that antenna will do. I think that was a tri-band antenna that they had the picture of. But yes, that is absolutely true. Okay, dummy load. Purpose of a dummy load is to prevent the radiation of signals when making tests. When you're experimenting with your radio, when you're tuning your radio, when you're testing your radio, what we don't want people doing, it's because it's practice, is to broadcast a signal on the antenna with, just a sound, because it interferes with other hams. So we have what we call a dummy load. This dummy load takes the energy from your radio and makes your radio think it's attached to an antenna. So all that energy goes into the dummy load, doesn't burn up your radio. If you have a radio and you don't have an antenna on it and you hit transmit, you hold the transmit down long enough, you will physically burn your radio up. There's a piece called the finals that physically overheats. Smoke comes from your radio, tears come from your eyes because you burned up your radio. And now it becomes a very expensive paperweight. So make sure that any radio that you ever have has an antenna on it before you hit transmit. If you don't, someone's crying. Whoever owns that radio is going to be crying because you'll burn them up. And it all depends on how much power the radio's set at, on how fast that happens. The handhelds, because the max is 5 watts, you might get 30 seconds before it starts doing permanent damage to the radio. The big radios that I have at home, the 100 watt or the 200 watt radio, it could be as quick as 5 seconds that could burn up a radio. So you have to understand, we have to have a load on our radios or we'll burn them up. Test signals from interfering with others, doesn't radiate a signal. Well, not much. That's true. It does radiate a signal, but it doesn't go very far. It just kind of, real close proximity of this. The load, the dummy load, this can is filled with mineral oil. Your antenna goes into this, and the mineral oil just takes in that energy. And if you transmit long enough on this, you can actually hear the oil boil inside these cans. I have one of these at home. In modern radios, we don't use these very much. In the older tube radios, that 1950s era radio that I have to use a dummy load to tune up my radio. There's a process I have to go through to balance my radio to make sure that I'm transmitting on the right frequency, and my antenna is balanced to my radio, so the signal that's going out is on the right frequency for the antenna. I don't get a lot of signal that comes back, so I'm tuning my radio. So instead of tuning it on the antenna, I tune it to this. All that energy goes into here. No one knows I'm tuning, and I can tune my radio. We use this for testing too. If I'm testing a radio and I want to put it on an oscilloscope, or I'm testing some of the other components of the radio, I'd put it on a dummy load. For practical purposes, just practical purposes, you'll probably never use one of these. For test purposes, yes, you have when you tuned up the Swan. For test purposes, you have to know that a dummy load, the purpose is to prevent the radiation of signals when making tests. So anytime that you're transmitting on a radio for testing purposes or for tuning up, you need to use a dummy load. That's what you need to know from this. Yeah, basically. Right. Because RF is energy. It's got to go somewhere. We don't want it to go out on an antenna to interfere with anybody. That energy has to go somewhere. It goes there. It's safe. This is a dry load. This is a wet load. It's heat thing. It's a heat sink, basically, is what this is. It's a big chunk of aluminum with fins cut in it. It gets really warm, really quick, depending on how much energy you put into it. It's filled with mineral oil. Correct.
Yeah. So this might help you out with it. Never mind. That's all I need.
She's good to go.
We're good then. I'll have to do that.
Love it.
I like that.
All right. That's antenna basics. How bad did I confuse you? Yeah. Yeah. It takes the place of it for the energy. Right. Yeah. Yep. Okay. So you guys are all good to go build an antenna? What's the formula for half antenna? In what? Megahertz. What's a quarter wave antenna? Why is it 234? Why is 468 the number for a half wave? There you go. Bonus points. There it is. That's way higher math than me. Okay, so moving on here. Do we need a break here, or we're doing this one? Roger that. All right, SWR, standing wave ratio. Fun stuff. What's impedance? What do SWR values mean? What does an antenna tuner do? And how do I measure the SWR? SWR is really important because if you have a high SWR, your standing wave, that's a bad thing for your radio, and you will trash a very nice radio very quickly. So we want to understand what is our standing wave ratio. So standing wave ratio is a measure of how well a load, an antenna is the load. Okay? How well a load is matched to the transmission line, such as an antenna load and the feed line transmission line. So that coax coming down from the antenna is our transmission line, and our load is our antenna. So we got to make sure that their relationship is balanced. If it's not balanced, signals come back from that antenna, reflects back from that antenna, comes down that line into our radio and burns things up. And big alligator tears come from the radio owner's eyes. So, come here. Okay, there we go. So, matched is the context, in this context, implies as impedance matched. Our transmission line, our coax, has to equal the ohms of our load. So our impedance is the measure of the opposition to the flow of alternating current in a circuit measured in units of ohms. Our impedance is measured by ohms. You will see this again. Impedance is measured by ohms. So if you're measuring your coax wire, if you go to, well, you used to be able to go to Radio Shack, can't go to Radio Shack anymore. Go somewhere that sells cheap coax wire. Coax is not coax is not coax. There's 75 ohm coax and there's 50 ohm coax. We play with 50 ohm coax. 75 ohm coax is the wrong size, bless you, is the wrong size for amateur radio. It's not, it doesn't protect our signals adequately. It's a cheaper wire. 75 ohm you'll see for TV stuff. For your cable television, 75 ohm wire, you'll see a lot of it. You go to Walmart, 75 ohm wire, you can buy that real cheap. 50 ohm wire, about twice the cost.
Walmart won't even sell the 50 ohms.
Oh, because it's twice the cost.
Yep.
Because there's twice the amount of material that's inside that stuff. So they don't even sell it. So you want to make sure that you have 50 ohm wire. If you get a multimeter, set it to ohms, put it across that wire, you will measure 50 ohms of resistance for every foot. That way you know that you have 50 ohm, or you can just look on the sheath and it says 50 ohm wire on it. That's the way I do it because it's a lot easier. So the impedance of most commonly used coax cables in amateur radio is 50 ohms. We want to know that. 50 ohms. Oh boy, will you see that again. Almost, yep. So a measure of how the opposition flow, we did this, why is this back? When impedance is matched, the greatest power transfer will be afforded from transmission line to antenna. When these like each other, all of your energy that's coming out of your radio goes out this cable to the antenna and out to the people you're trying to talk to. If it's mismatched, the signal comes back into your radio and big alligator tears come out of your face. Okay? When impedance matched, some transmission power will be reflected back down the transmission line. Bad day. SWR comparison of forward power to the reflected power of the transmission line. We have SWR meters that'll do this math thing that we're about to show you automatically. This is going to, you forget to bring yours. We're going to show you how to figure this out mathematically because there are what we call dual needle antennas. You have a needle that measures your forward power and you have a needle that measures your reflected power. And when the two needles go up, wherever they intersect, that's your measurement. Easy peasy. They make cheaper antenna or meters that only have one needle. So you transmit, measure your forward, flip a switch, measure your reflected, do this math equation that we're going to show you, and then you figure out what your SWR is. Not as easy peasy. I don't like math. I'm lazy and I like the double needle things. So that's why we need to know this. SWR is. So this isn't a joke. You really need to know this formula. So our SWR is the square root of your forward power plus the square root of your reflective power divided by the square root of your forward power minus the square root of your reflective power gives you SWR. Excel's my friend. I've actually built this in an Excel spreadsheet, so I just put in the numbers, does it for me. Okay, so a perfect impedance match between an antenna and a feed line is no reflective power, or 1-to-1. I want a 1-to-1 ratio. That would be my SWR. My SWR is 1-to-1. It's perfect. Can't get anything better than that.
Hey, really quick, so you guys don't freak out, that formula is not a test question. However, this is exactly. So you don't have to remember the formula. You just got to remember how the formula works with everything. Just a heads up.
Good clarification.
Yep.
Thanks. Thanks. Okay. So the approximate SWR above which protection circuits in most transmitters begin to produce transmitter power. In these radios, the handheld radios, the mobile radios, the modern radios, there's computer circuitry that has a built-in SWR meter. Every time you transmit, it's measuring your signal. And it's looking for this, the 1-to-1. This, it's doing the happy dance. If it measures 2-to-1, it'll reduce your power automatically. It'll take you from 100 watts, take you down to 50 watts, which is really interesting. I've had this done to me actually on my radio. I was talking on my mobile HF in my truck, and I noticed, I'm always watching my meters, but I noticed that I wasn't transmitting at 100 watts anymore. It was at 50 watts. It annoyed me. Couldn't figure out why. transmitted again. Sure enough, went 50 watts. And the station that I was talking to says, I don't know what you did, but I lost you by half. Like, well, yeah, I lost half my freaking power. Hold on a minute. Pulled over, and where's my antenna? No, the antenna came loose. The screwdriver. Oh, there it is. This antenna is on the roof of my truck. There's a bolt in the bottom of this that screws into my truck. It was a turn and a half loose. I pulled over, turn and a half, tightened it down, 100 watts, because my SWR was off. That loose connection screwed up my SWR. The radio saw it, cut my power down so I didn't burn up my radio. Tighten it down, went back to 100 watts. The guy says, hey, you're back. Welcome back to the world. I'm like, yeah, tight antenna will do that. So, SWR 3 to 1. No longer be able to provide a transceiver matching impedance. There's I call it a magic box, but there's a box that you can get that has loads in it that you tune the loads to trick the radio into thinking that your mismatched antenna takes that extra energy and displaces it in the antenna tuner. So I can take the chain link fence that's out here on the around the parking lot. I can connect that to my antenna tuner to my radio. I can adjust my antenna tuner to balance my antenna, and I can use the chain link fence as an antenna. It's fooling the radio. So poor antenna tuners won't tune above 3.1. So that chain link fence, I guarantee you, is above 3.1. It's what we call infinity. I'll probably never get poor ones. I've got a couple nice ones that I know I can tune up because I've done it. But again, what you get what you pay for. So if you antenna tuner, $25 is antenna tuner. That's great. I'm not paying the $150 I just saw. Well, it's a poor one, and you're probably a crappy antenna to perform well. Antenna matcher. So you want to have a good antenna tuner. 1-to-1's perfect. 2-to-1, our internal circuitry in our radios can see that and step down your power. The 3-to-1, they can't see that, and down your, they'll either come with an error code on your radio, or it won't let you transmit. You'll hit transmit, and it just pops, goes right back down to nothing. You're like, what the heck's going on? You probably forgot to connect your antenna, or the antenna is mismatched. So 3-to-1 is really, really bad. You don't ever want to. 4-to-1 or higher, we call that infinity. When I go like this, it's because the double swing needles, they go straight up. We call that infinity. 4-to-1 or higher, that's infinity. Impedance mismatch, yeah. Score, not so much. Yeah, this is bad. Yeah, exactly. Or just connect the antenna. My dad does this every now and then. He'll call me on the VHF radio. Something wrong with my HF. What's the matter? My SWR is really, really high. Is it at infinity? The needle's going like this. Yeah. Did you connect your antenna? Yeah. Hold on. Yep. Okay, works now. All right, Dad. Welcome back to the world. Well, when the thunderstorms come through, he disconnects his coaxes because these things are on our roof and they're big lightning attractors. Yeah. So he disconnects it, and a couple days later, he'll forget that there was a thunderstorm and get on the radio, and he freaks out. And I'm like, 2 days ago we had a thunderstorm, right? Hold on. Okay, I'm back on. All right, have fun. So yeah, we do that a lot. This is an antenna tuner. Again, these controls balance my antenna, and there's instructions to go with it. I'm not going to get into it because it's kind of out of what we need to talk about, but just know this is an antenna tuner, and it tricks the radio in thinking that you have a balanced antenna. So it goes in the middle of your circuit. Antenna tuner matches the antenna system impedance to the transmitter's output impedance. So you got your radio, the coax from your radio goes into the antenna tuner. You adjust this to where the needles get down as close to 1-to-1 as you can possibly get. Coax goes out to the antenna, signal goes out, life is good. There is a quality difference. If you're using an antenna tuner, you don't get the performance as you get out of a balanced antenna. So if you go through the time and the math, and cut your dipole for that band that you want. It doesn't need an antenna tuner. It's cut for the resonance of that frequency. And you use an SWR meter to confirm your math to make sure that you didn't read the tape measure wrong. That. So you want to use an SWR meter, but you don't need this antenna tuner. That antenna cut to the frequency will outperform a wire that I put out that I'm using an antenna tuner, because the antenna tuner reduces the performance. Does that make sense? Because you're tricking this thing. You're lying to it. And there is a trade-off for it. Okay, so in this case, it was a 5-to-1 ratio because it's only a 10 ohm impedance. So it gave a 5-to-1. Goes to the antenna tuner. We do magic, makes it 1-to-1, calls it 50 ohms. The radio's happy, lets you transmit, and you have a good day. You just don't have as good of performance as a good quality antenna does. In some cases, it may be okay to operate with a high antenna SWR. Most transceivers don't like to see SWR of more than 2-to-1. If you ever have an SWR reading of more than 2-to-1, figure out what's wrong with your antenna before you keep transmitting, or you will ruin your radio. And that's that point of no return. You can install antenna tuner in the line for the output. Oh, thank you, Chris. I need that. Yeah. Nope. It tunes the antenna to trick the radio into saying that this is a balanced antenna. The modern radios have that. Yeah. Sometimes it's on a graph that you can see. Sometimes it's a needle, depending on the type of radio that you have, and who makes it here. Gimme. Thank you. Oh, good. Thanks. It is. Yep. Handhelds usually don't have a built-in SWR. The mobile that I have out in my truck does. And at break or after class, if you guys want to, we can throw that antenna on my truck. I can show you what it looks like. Absolutely. Absolutely. It's just scaled down a little bit. Handhelds don't have it because we have fixed antennas and we're only on either VHF or UHF. So all the internal electronics is all, oh, those computers do amazing things, but there's not a need for it. That's the thing I'm getting at, because you're not the HF radios, because I can go from band to band to band to band. There's a need for the SWR because I have to have the right antenna. That's a VHF radio. It needs a VHF antenna. I'm done. The radio that I have out there, because it's a 2-meter radio, I put a 2-meter antenna on it. I'm done. The radio that I have out in the truck is a 10-meter, 20-meter. I always forget. I'm gonna cheat. 40 meter. That radio will do that. This antenna will do that. This is called a screwdriver antenna. So there's a power that goes on here, and there's a little motor inside here. This outer sleeve moves up and down, and you can see the copper coil that's in here. This is all HF. Yep. So as this sleeve moves up, it adjusts the load of the antenna. So I can tune my radio with this antenna, because I'm fooling the radio to think that this antenna is really longer than it is, based off of this copper coil and how much of the copper coil is used. Does that make sense? Right. 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 You can buy these sticks. You can buy this to 10 meter, 20 meter, 40 meter. So, okay, now I want to go from 10 meter to 40 meter. I got to run out in my car, unscrew this, put that in the trunk, pull out my 40 meter, screw that in, then I got my 40 meter band. Yeah. That's it. Right, right. Now, if I want to cheat and I want to use that 10-meter dipole, and I want to go to 20 meters, I need one of these. I can make the radio think that's a 20-meter dipole when it's only a 10-meter dipole because I'm using an antenna tuner. Mm-hmm. 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 Probably have a loose connection. Or there's water in the coax.
There's two major problems with that, especially if you get brand new stuff. You got a brand new radio, brand new antenna, all that. The connection's loose, or you have the wrong ohm wire. You may not have gotten the heavy 50 ohm that we keep talking about for the coax. You're using the cheap stuff from Walmart, 75 ohm. That will make your mismatch.
Yep.
If it's a brand new radio, it should not be a radio issue. Correct. It'll be something with your wire or your antenna, one of the two.
Yep.
And if you have a specifically cut antenna, then it's only the wire problem. Your connections are loose or you have the wrong ohms. Easiest way to check, look at the wire itself. It tells you 50 ohm.
Or if you get water in the connections, water screws it up.
Oh, yeah.
Right. Right.
For instance, the dipole that he has on his shop, the 102-foot dipole, 50 or 104 foot, 52 feet each side. That's not matched to anything specifically. So he has to have the antenna tuner to make the radio think that it's matched because they're not a specific cut. This way you can use one antenna for all the different bands instead of having an antenna cut for each band and you're physically switching them. It saves space.
Mm-hmm. Oh, yeah. 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 Now, we talk about that. I'm going to go on a rabbit trail a little bit, but it's not quite because it's still on antennas. We have our 10-meter dipole right here. Okay? So that's cut for 10 meter. If I take my radio, put it on 10 meter, tune up to 10 meter, my internal SWR is going to give me a 1-to-1 because that's cut mathematically to the antenna. It's going to love it. Here's what I have at home. I had the 110-foot wire. It was just a long wire, 110 foot, 55 feet on each side. It was fed in the middle by a coax. I used an antenna tuner for every band that I wanted to. Why did I have 110 foot? Because my shop's 110 feet long and it has a corrugated steel roof on it. I was experimenting and I was playing with antennas. I had a ball with this antenna. I got all kinds of cool contacts with this antenna. So I had that for a couple years. I got bored because that's what I do with antennas. I got bored. And now I built what we call a fan dipole antenna. So I have a dipole. I don't remember the dimensions, so forgive me. I'm not going to give you the actual dimensions because I don't remember. But this is 10 meter, 20 meter, and I take that back. This is 40 meter, 20 meter, and 10 meter. I did that backwards. I did the math, calculated the length. Okay, so cut to length. These are 40 meter, 20 meter, and 10 meter. I don't have to have an antenna tuner. I can bounce from those between those three bands on my radio without tuning anything. All at once. Yeah. All at once. All these are connected to one coax that goes to my happy little radio down here.
It resonates.
Yeah. There's a knob on my radio that I say I'm on 10 meter. Flip it to that, and I get all the 10 meter frequencies. The electricity, because of the way electricity is, it finds its path of least resistance, finds its element in the antenna. It's magic. It's just the neatest thing on the planet. Finds its own thing all by itself, radiates out. I don't have to do anything out here. So then I get tired of 10 meter and I switch to 20 meter The electricity finds its path of least resistance because this is resonant to that frequency. It likes this. This is more resistive. This is more resistive. This is least resistive. It loves this. It radiates out on that. Because of the construction of these three, I get a bonus of, shit, I forgot. I was going to cheat because I don't do it very often. 40, 20, 15 meters. These combined give me 15 meters. Because of the way it's cut, and when you do the math on it, it makes sense. The electricity goes out on all of them, and I can tune up to 15 meters without an antenna tuner. The fan dipole antenna was one of the neatest things that I stumbled across. A guy down the street from my dad's house had one, and I'm like, that's cool. Did some research on it. Really easy to make. Took me an afternoon all by myself, and made this thing out of electrical wire. Went down to Lowe's, about 100 feet of number 12 single strand copper electrical wire. It could cost me like $15, $16, something like that. This antenna, and I looked it up on HRO to get this antenna commercially. It's over $100. So for $20 in the afternoon, and I had some fun. It was cheap fun, and I've had that up there for a couple of years now.
I would have brought mine in,
great.
but mine's in use too.
Yeah, I actually made one for field day, so I've got a portable one now, so I can take it out with my Go Box, and I don't need the antenna tuner. I have one, but I don't need it. So that's what I'm saying. Antennas, you can experiment with it. A J-pole that I made at my dad's house that a couple old hams said, that will never work. I don't like hearing that. I'm going to make this damn thing work. So I kept puttering with it, got my meters out, my analyzers, did all this stuff. My dad's been using it for 10 years. So the antenna that they said, that won't work. And he outperforms these guys all the time. And he loves to remind them, this is that antenna that you said won't work. They get all kinds of quiet. Yep. The nice thing about ham radio, it can be an expensive or it can be a poor man's house. Depends on what you want to put into it.
Okay, we got to keep moving this one along.
I'm sorry, I got off on a tangent. I love antennas if you haven't figured it out. I
and
really,
now you see
really
why
do.
We put him on the antennas chapter.
So this is a dual needle antenna SWR meter. So this needle measures my forward power, the energy that's going out to the antenna. This is my reflected energy. That's the energy that hit that load and is radio. We want this as low as it goes. So where they intersect is my SWR. So in this particular image, this is actually it's almost a 5-to-1 on this image. Is that good or bad? Not good. That radio going to cry. You're going to cry. It's going to be a bad, bad day. So we want this intersection to be down here on the scale where there's a 1, there's a 1.2, 1.3, 1.4, 1.5. We want it down here at the 1. The forward power is how much are you transmitting. This particular scale is on 20 watts. The one I have at home is a 200 watt. And there usually switches that you can switch. Well, here it is, 20 watt or 200 watt. So you can change your scale. All depends on how much power you're putting out. That handheld puts out about 5 watts max on a good day. My radio in my truck is 100 watts on a good day. That's the max power that it will do. My radio at home is a 200 radio. And I've got a 1,000 watt amplifier next to it in case I really want to reach out and touch somebody. Chris hates it when I bring that up, that I have an amplifier. It's a whole different thing. So antenna analyzers. These are great tools, if you're going to do experiments with an antenna. That whole dipole, remember, we have to cut the dipole if it doesn't resonate right. Got to cut it down to get it to resonate in the frequency that you want. This antenna analyzer, can be used to determine if it is resonant to the desired frequency using this measurement. This thing produces a very small radio frequency, like 1/8 of a watt, very small. But it measures what the SWR is. So you can plug this thing in, and it runs AA batteries, plug that into your antenna, dial in the frequency that you're testing, and the SWR will be measured on these meters. And that way you know, is it my antenna that's boogered up? Or if I'm building an antenna, it saves your radio. Otherwise, you got to put your radio on it. You got to hit transmit. Ooh, that was 5 to 1. That sucks. Go cut a little bit and hit transmit again. That's a bad way of doing it. You want an antenna analyzer. It's a lot safer, and it's safe to do this. What's electronics parts store here in town called OEM, and they sell by the bucket loads, and I'm not kidding you, by the bucket load, these things, the rubber duckies. But they're literally in 5-gallon buckets sitting on the floor. They just take them off radios that they scavenge and throw them in the bucket. And you just say, what frequency is this on? They have no idea. So I take my antenna analyzer in there, and I find an empty bucket, turn it upside down, and I sit down and I start screwing antennas into the antenna analyzer and find the antenna that I want in the length that I want. It drives them nuts because I'm in there for a couple hours going through their pile of crap. But when I walk out of there, it costs me $1.50 for an antenna instead of the $30 that you pay for them online. Just saying. These things pay for themselves really quick if you're going to play with antennas and fixed radios and stuff like that. So that's why we have antenna analyzer. Test question, antenna analyzer can be used to determine if an antenna is resonant at the desired frequency. That's why I can test my rubber duck to find out what it's at. This is called a bird meter or an SWR meter. It's a single needle. So I measure, there's a plug that goes in here. It's a directional plug, has a big arrow on it. So if I point it this way and my antenna is hooked onto this side, it measures my forward power. If I turn this knob and point the antenna back towards the radio, it measures my reflected power. So forward and reflected power, single needle. I take my measurement on forward, take my measurement on reflected, plug it into this formula, my SWR. Okay? Old school. I have one of these meters. Actually, my dad has one of these meters. To buy this new is about $500. They're crazy expensive. They use them a lot in commercial radio because they measure very RF. This meter here, anywhere from $50 to $150. You can buy a dual meter antenna, SWR meter for amateur. A lot more economical than that thing is. More practical than this thing is because you transmit, it gives you the signal right away. So there's no question about it. Highly, highly recommend this. I own. So just one of those things. All right, SWR, coax connectors. We'll fly through this. So this is our coax that we were talking about earlier. You have your inner connector, insulator, braided shield, outer jacket. 50 ohm shielding is this nice, tight, beautiful weave. That 75 ohm is about half that material. So you see a lot of insulation, inner insulated material you can see through the shield. Because it's only 75 ohm. It's not as efficient as the 50 ohm. So make sure you get the 50 ohm stuff. Works better for us and it balances things out. So cable, 2 conductors, commonly used RF signals. Feed line amateur radio because it's easy to use, requires few special installations and considerations. Very, very flexible, very useful wire. It's important to have a low SWR in an antenna system using coaxial cable to allow the efficient transfer of power and reduce line loss. If this center conductor is really small, some of the cheaper cables, and I can't remember the rating for it, has a real small, almost like a single conductor center conductor. That's where all your heavy power is going. And if you're doing like a 200-watt transmitter through that, you'll literally melt this wire. It becomes a fusible link and becomes really ugly. So you don't want that. All right. The shields prevents coupling of unwanted signals to and from your wire. So this shield literally keeps that RF signal here on this conductor and it doesn't radiate out on the cable and you get RF in your shack or in your car or whatever. So it protects you. Feed line loss, power lost in coaxial cable is converted to heat. If this conductor is really small and you're putting lots of power through it, it gets really hot. If this coax is, say, a couple 100 feet long, you got, you put your antenna on the backside of your property, in between your antenna and your radio, 500-600 feet. This is going to get hot because of what we call line loss. It goes a long ways, and it's pushing that cable or that power, and the power has to go somewhere. You get line loss. This thing will get real hot and you can melt it too. Generally, this is in signal frequency. In your larger diameter RG8, that's this RG8. It's where the size that they call it has less loss for a given frequency than the smaller RG58. So RG8 is better than RG58. Just remember that. The new stuff that's out is RG8. The physical diameter is just a little bit smaller. It's a little more flexible, but it has the same characteristics as bigger cable. Great stuff. It's about $1.50 a foot, and it's worth every penny. I'll tell you that right now. But just remember, RG better than RG58. It'll help you with that test question. VHF and UHF are air insulated hard lines. Has the lowest loss. This stuff is most common for VHF and UHF. You can use it on HF. It depends on how long of a distance that you're running. You can get bigger stuff and how much power. If you're doing like 100 watts, you can RG8. If you're going to do 200, 400, or 1,000 watts, you want to get bigger stuff. They call it LMR. It's just a bigger cable. The center conductor is bigger. The shielding is bigger too, but it can handle that heavier power. The plastic has some. It's like Swiss cheese. This insulator, instead of being that solid foam, it's like Swiss cheese that goes through there. Yeah. Moisture contamination, the most common cause of failure in coax cable. If you put a connector into an antenna outside, make sure you wrap that connector with tape, or what we call liquid tape. You can get these bottles of liquid tape at Big R. Some Walmarts carry it too. It's black, gooey stuff, but it's liquid tape, and that's what it's marketed as. I always wrap my connector with tape, and I paint on the liquid tape to make sure I cover everything with it, and it makes a nice tight seal so moisture doesn't get into it. You get moisture into your connector, either from condensation, from rain, snow, whatever. You'll get a 5-to-1 SWR like that and not know why. Moisture. And the coax, the braided cable of the coax, acts like a wick and will wick that moisture from your connector down into your cable and shorts out your cable. So you could wind up cutting a 3 foot of your cable off to get the dry cable. So moisture, bad stuff. Disadvantage of air core, or air insulated coax is that it requires special techniques to prevent water absorption as compared to the more common foam or solid dielectric types. So that solid foam is less susceptible to moisture infiltration than the air coil stuff. That stuff that looks like Swiss cheese, you can get condensation inside that cable with very tight connectors. So it's very temperamental stuff. So light can damage jacket of your material, allowing water to enter your cable. So the jacket should be resistant to UV light. When you buy coax, if it's going to be outside, make sure on the labeling it says UV resistant. If it doesn't say UV resistant on it, the sun will break it down, and it's just like anything else. Sun will rot it, lets moisture get into it, screws it up, and you probably ruin a really nice radio.
If you're looking for cable and you're going to, and I'm just using this example, Walmart, if it says outdoor cable, it does not necessarily have the UV protection on it. It's just rated that it can go outside. It doesn't mean that it can stay outside for long periods of time. So don't trust the outdoor rated cables. Make sure the cable itself says UV on it.
Yep. Coax connectors exposed to weather should be sealed against water intrusion to prevent increased feed line loss, which I was just saying. Wrap it in tape, cover it with electrical tape. Yep. Wrap it with electrical tape and cover it with liquid tape, and that will be a connection that will last for a long time. I'm an old electrician too, by the way, so I did a lot of that stuff. Not very hard at all. Not very hard at all. Matter of fact, an X-Acto knife. That's why You wrap it with tape first because on your, that connector has a knurled end to it. And if you just put liquid tape on it, it gets down in all the grooves, the threads, and all that stuff. That's a pain in the butt. If you wrap it with electrical tape to cover it, then seal the electrical tape with liquid tape. A razor blade cuts across the tape, peels it all off. It looks brand spanking new when it comes out. I had a connection that was 5 years old that I did this with, opened it up, and it literally did look shiny new, like I bought it. SMA connectors, we talked about that just a little bit ago, most commonly found on your radios, your handhelds, BNC connectors. You got a female and a male. Common on handheld radios, good performance at most amateur frequencies. There's no difference in performance between the two connectors. It all depends on the manufacturer, which one they spec'd out when they built the radio, whether it's a BNC or an SMA. These were, 5 years ago, were the new guys on the block. This was kind of an industry standard for a long time. Now they've been around long enough, everybody's using them. So the SMA is real common. This is an N connector, most for 400 megahertz and above. You see it mostly in commercial use, just because it's a thicker connector, more robust. It'll hold more stress. The most common connector that you'll find on our amateur radios is a PL250 or the SO239, which is the male side, and it's the female side of the 259 connector, commonly used in HF, VHF, UHF. Most commonly seen in amateur radio is your 259. We see these quite a bit on handhelds. This is quite a bit on handhelds, more on commercial. You just need to know the difference between N, 239, BNC, and SMA. These are the two test questions. You can get adapters to make these work on one another. I have an antenna that has an N on it, and I have an adapter on it to go on a 239. The more adapters you use, it reduces your performance. So you want to get away from adapters if you can. Loose connection can screw up your SWR, especially if you have an adapter. The more adapters is more of these screw-on connectors, more chance of a loose connection. So again, you want to have as few of those as you can. So kind of looking overall, this is my dream house. I have a dipole antenna, a vertical antenna, another vertical antenna. This is a multi-band. See the traps that are in this? I have several bands that this will work on. My beam, or VHF beam, and here's my HF beam on a 30-foot tower. The cool thing is my wife says, go for it. I like it. Kind of nice.
I don't know what my wife would say. And there's my answer.
Well, that's just,
I know, right?
you chose poorly. Was that my outside voice? I'm sorry. This is Christopher's dream car.
No. This is Becca's future car.
All right. Questions, comments, concerns on coax and connectors. I went through that kind of fast, but they're pretty straightforward. Yes, ma'am. Directional watt meter.
That bird.
That was that bird. That was this thing.
I can pull it up.
Yeah. Yep. Perfect. This one right here. So forward and reflected. That's your one-way watt meter, and this is your dual needle watt meter. Okay.
Good question.
Got to know those because those are test questions. Okay. Anything else? Yeah.
Well,
now comes a break.
I was gonna say, I'll tell you what, we'll be nice to y'all, and we'll give you. How about, let's see here. Yeah, let's do 10 minutes. Let's meet back here at actually 6:55. How about that? 6:55. We'll be back to start. Okay, so it's been 10 minutes. We're going to go ahead and get back started again. This time we're going to be It's Electric, get a little more into Ohm's Law and everything. And we welcome back the instructor, Will, back to the stage. So let's get rolling.
Great. So with chapter 8, we're going to learn electric basics. It's not as ominous as it sounds. We're going to get into Ohm's Law, power law, and learning about electrical measurements. No, it's not. It's fun. I love this. We're going to figure out how is electricity like water, and what are the units of the basic electrical measurements. What's the difference between AC and DC? What are conductors and insulators? So how is electricity like water? Well, this is kind of a convoluted picture, but if you think about a water hose, a lot of the same, I hate to use the word measurements, but a lot of the same labels can be extrapolated from using a water hose to electricity. So your water flow, and in this case electric flow, is your current. I'm not going to get into the pump being the battery and all that. We're just looking at electric flow. Your pipe would be your wire. Resistance is whatever's creating, whatever's resisting the flow of the electricity, or in this case the water. So in this diagram, your battery would be your pump, would be pushing out the water. Your pipe obviously would be equivalent to our wire in electricity. The water wheel is creating resistance to that flow. If you have a constriction, a kink in the hose, you also create resistance to that flow. And then your water flow is the current. So you transported or transcribe that to electric current and flow. So again, you have your electric current, which is the flow. Your wire is the hose. Your appliance is what creates your resistance. And obviously you can also have a resistor which creates resistance. Test question: voltage represented by the letter E is equal to your water pressure. Volt is a unit of voltage. Voltmeter is what measures the voltage, or the unit of measurement. Current represented by the letter I. It's the quantity of flow. So it's how much is moving through a given point. It's measured in amperes, measured in ammeter. And then resistance. Resistance is the amount of drag or an obstruction to that flow. It's measured in ohms, and it's measured with an ohm meter. Yes, ma'am. This is a direct current example. I'm going to get into that here in a second. No. Oh, yes. Yes. And with direct current, your resistance is going to be a little bit different. Well, it's measured the same and it works the same, but because with alternating current, you're going both directions, and direct current, you're going one direction. So you have that resistance to flow in that one direction, which is the direct current. So it's basically for the diagram, for the purposes of the diagram. So yes, ma'am. That's correct. Correct. If it uses a battery, it works on direct current. If it's using something that's powered by the wall outlets, that's alternating current. Little bit of trivia: these lights are flickering at 60 times per second. So the current's going back and forth 60 times per second. Yes. And again, it's alternating current. Direct current. And your car, it's moving one direction. Yes. So do we understand the symbols for the different items and the different measurements? Okay, voltage term for electromotive force is EMF. And that's what's basically, to put that in a nutshell, it's what's moving the electrons in whichever direction you're going, either directly or alternating. Mobile transceiver, well, that'd be portable, same thing. Requires battery operation, 12 volts in a mobile because it's in a car, and it's going one direction. So there's your car battery. Just think of this as your radio. So you have your car battery sending the current in one direction, goes into your radio, and goes back to the other end of the battery. And it's just a big circle. Current is the name for the flow of electrons in an electric circuit. Now here's where we're getting into the difference between AC and DC. So direct current, it's moving in one direction and one direction only. So a good example with regards to this fan, if I plug this in this direction, the fan will turn, let's just say it turns clockwise. If I reverse the polarity of the wires, meaning I'm moving the current the opposite direction, the fan will turn the opposite direction. Because I'm moving it in a different direction. And yes, correct, which is what I'm talking about in DC. Yes, in DC. So take this out. So in this diagram, if I reverse this direction of flow, I change the wires, the fan will turn the opposite direction. So we have direct current means one direction and one direction only. Alternating current, excuse me, reverses the direction within the circuit. So it reverses the direction on its own. So as you can see here, it's kind of hard to see because it looks like it's just jumping, but the current's going one direction and then back the other direction. Back and forth. So that's the difference between alternating current and direct current. Anything that's plugged into your house is alternating current, or AC. Anything that's running off of a battery is direct current, or DC. And in our country, in the US, everything happens at 60 times per second, or 60 cycles. In Great Britain or Europe, it's 50. No, all AC. If it's plugged into your house, it's alternating current. Alternating current. And in the US, everything, this reversing of direction happens 60 times per second in this country. In Europe, it happens 50 times per second. Okay.
Trivia point.
Yes.
Back in the day, DC was the first electricity. That's what they first. It was DC. Right.
Correct.
What they found was DC cannot be transmitted over long distances. So that's where AC came from. And that's why we have AC in our power grid system now.
And AC was actually came to be from Nikola Tesla that did his experiments here in Colorado Springs. And the experiments that he did here in the Springs created the AC concept that was brought up to the World Fair in Chicago. And they powered the entire World Fair in AC current. But Edison was the one that did DC, and none of his stuff worked, including his lights, into AC. So it all had to be redesigned to work all together. Yep,
Well,
that's where we got this.
Edison actually, in order to try to, and again, it's just a trivia point, in order to defame Nikola Tesla, he killed an elephant using alternating current. And he was just trying to show the public why they shouldn't go with alternating current because it's too dangerous. So, but again, alternating current going back and forth. I mean, obviously we can't see the flickering, but it's happening 60 times per second, 60 cycles. AC frequency, the number of times per second the AC reverses direction. Impedance. The way I remember this is impedance is resistance. So you're impeding something, you're resisting something. So impedance is a measure of the opposition to AC current flow in unit of ohms. So again, it's the resistance, and that's a test question, and it's actually part of two test questions, but it's the impedance is you're impeding the flow, resisting the flow. So that's how you remember that it's part of resistance. There's no difference. Impedance is typically used when you're referring to alternating current, but it's just resistance to the current. Resistance is typically referred to, the word resistance is typically referred to in direct current, but they're both resistance, and they're both measured in ohms. The current. Right.
Amps measures.
Alternating. Say it again.
Think of it this way. Think of it like water pressure. Okay. So if I have a pipe that has 80 psi, pounds per square inch of pressure, that's like having 12 volts of electricity, 12 volts DC electricity. That's my psi. But I'm flowing 20 gallons a minute of water. That's how many amps I'm pushing.
That's your current.
So if I've got a 12 volt DC circuit, that's my psi, and I'm drawing 10 amps of current, that's how many gallons of water I'm running. Does that make sense? No, voltage is voltage, whether it's DC or AC.
Right.
Amps is amps, whether it's AC or DC.
Battery, if I were to make it where I can get 12 volts out of that, 12 volts. 12 volts is 12 volts. 10 amps is 10 amps. The current or the direct or alternating current is basically just which direction that power is going, that electron is going.
We'll go back a slide. So that resistor that's in the DC circuit, if I had a 12 volt battery and I put a resistor in there to reduce the power down to 6 volts, my resistor is holding back that other 6 volts of electricity. That's what a resistor does. It lowers my amp or my voltage. Yep.
So that way you're not damaging the appliance. A good example of that is, without in depth to it, your cell phone. Your cell phone runs on a 3.5 volt battery, but when you plug it into the wall, it's 110 volts. So if you don't want to fry your phone, there's a transformer.
That's going through a transformer.
Right. There's a transformer in there that steps it down so you're not frying it. It's taking it kind of like a resistor would, taking it from the 12 volts to 6 volts. Well, the similar situation occurs with those transformers on the big black box on your cord. All it's doing is it's changing the voltage from what's coming out of the power source to a voltage that won't harm your appliance. That's what the resistor does. So if I've got, like he said, 12 volts coming out of this battery, and that's an appliance that runs on 6 volts, this is stopping that battery from frying that. If I hook it straight to the battery, I'll burn it up. So the resistor basically just takes a little bit off. It bleeds some of that off so it doesn't harm your appliance.
And they get warm because you're taking you're taking power away. So that's why some resistors are really big. It's what a dummy load's a great big resistor. That's what a dummy load is. Yeah, absolutely.
And if you
Yep.
Correct.
Because what they're using is a lot of the resistors to step it down to what you need. Yep.
Conductors, obviously different metals. Metals are some of the best conductors. Copper, aluminum, silver, or any alloy thereof. Insulators, glass is what, I think we're all old enough, most of us old enough to remember the glass resistors up on the power poles. They're highly collectible now. And all it is it's something that resists the current so that you're not losing, it's staying within that line and going where it's supposed to go, and you're not losing it into your
the electrician part of me comes out here. Your insulator.
No, I'm talking about the insulator.
That's an insulator.
The glass insulator.
Yeah, the insulator prevents, because those glass insulators, the wire that ran on those transmission lines was uninsulated wire. So they had to have an insulator that protected the electricity from shorting out on the pole. The plastic insulation, like on this wire here, it has plastic insulation on it. That's to protect us from touching the electricity or from it shorting out. It doesn't prevent electricity from bleeding off of the wire.
No. What I was trying to get at was what you just said. It stops it from going down the pole, into the box, into the wall. It stops it.
Touching people.
Yeah.
Yeah.
I hadn't gotten there yet.
Yeah. Okay. I was hearing bleeding off.
No.
It doesn't stop
electricity
from going.
Poor birds.
No. In fact, if you go out to the high tension lines, you can take these poles and hold them up, and they'll turn on because of all the power that comes off those. Yep. And basically, it's just different materials. Just like you have the materials that are good conductors, you also have materials that are really good insulators. That's the basics of electricity. Anybody have any questions over amps, ohms, impedance, any of that? Okay. This is my favorite part. So again, E is our voltage, I is a current, R is resistance. These are going to be very, very, very important in terms of the test. You will see multiple questions on this. So this is basically the same thing they have there. They got it in a triangle. I always put mine in a circle. And to get E, or your voltage, you're going to multiply I times R. Okay? So if you want to get voltage, you're going to multiply whatever the number of your current is by the resistance, and that'll give you your voltage. If you want to...
An easy way that I use to remember the EIR stuff, E is energy, R is resistance, I is the only thing left, so that's amps. So E is energy, or your voltage, R is resistance or ohms, I is current or amps. That's if you're trying to figure this out, I always, what is E again? What is R? That's just the way I remember it. I don't know if I'm confusing you or not, but that's how I remember it.
That's what I remembered as well. That's how I did it.
It's energy.
It's energy.
Energy, it's voltage. Yep. R is resistance or ohms, and I is your current or amps.
Okay, and then with the other two, it's division. And you always start with E. So if I want to find R, I'm going to divide E by R. So one of the tricks that we use is cover up what you want with your thumb, and then you're going to follow the formula for the other two. If you want E, you multiply I times R. Okay, does that make sense? And if you want I, you're going to cover up I, and it's E divided by R. Does that make sense? And the same thing with R. If you want R, it's E divided by I.
To kind of help with that too, help with me, how many people remember algebra? Yes. Yep.
Yes.
If you look at the triangle, the line going across is like your fraction. Your fraction is just a dividing deal. Anything that's not that, it's multiplication. Because I'll tell you, when you get to the test, you can write this on your scratch sheet after they say let the test begin. You can write it down, because I guarantee you there will be a math problem that will inquire either this one or the other one. And I'll tell you that when you're in there looking at it, you'll kind of forget which one's which. So
on my test day, when I sat down and they said you could begin, that's the first thing I did was wrote these down. And I had 3 questions on Ohm's law, and I had 1 question on power law.
Oh, you're lucky. I only had 1 of each.
Right.
Correct.
Exactly.
Correct.
Exactly.
When they, yep, nope. Yep.
Yep. Yep.
Yeah.
I'm telling you, at least for me, and I'm not speaking for these two, I needed to do that brain math. It was absolutely imperative. It was imperative. Yes.
Yep.
So let's do an example. If I've got, what is the voltage across 10 ohm resistor if I have 1 ampere of current? So what am I looking for? Right, I'm looking for E, so I multiply. Okay. I know, right? Not my color. Right. They went to the... They went to the budget salon. So
they used a hammer.
If I have current flowing through a 100 ohm resistor connected to 200 volts, what is the current? So what am I looking for? Okay, so cover that up, and what's my action? Okay, so what would it be? 2. It's an ugly thumb. Yeah. Right, right. So what would the resistance be if I have 12 volts and 1.5 amperes of current? What's the action? What do I want? What am I looking for? Okay. Which would be 8 ohms. Very good. So we've got Ohm's law. That's it in a nutshell.
Okay, those 3 questions you just went through, that's how they're worded
Yes.
in your test. There's no take the decimals and carry and all that. They're easy, straight ones to work with.
And what I do, and I do this not just with Ohm's law, but I do this with a lot of the problems I have. Like I'm in the police academy now, and I do it with a lot of tests we have. This is a lot of minutia. So I take out what do they want, and what do I have, and then I go from there. The rest of that minutia can be distracting and confusing. So I take out what I want, what they want. I look at what my components are, and I remove the minutia. So power is the rate at which electrical energy is used. It's represented with the P, and it's measured in watts. I is obviously the same, it's current, and then E is the same, it's volts. So here's Ohm's law. This is power law. Yes, yes.
And we'll get into
most
that
of that comes
the
down
next
to
one.
if you're trying to build something, and I'm going to supply it with 12 volts. Well, if my appliance can only handle 4 volts, I need to know how much resistance to put in there so I don't fry it. So it's basically just you're using the relationship and the ratio is what you're trying to create. So we're going to do the exact same process for this. P takes the place of E, and E takes the place of R. And then it's the same process. You cover what you want, and do the process for the other 2. So how much power is being used in the circuit when the applied voltage is 13.8 volts DC and the current is 10 amps? Okay, so what do I have? What am I looking for? Right, so I multiply 10 times 13.8, which gives me, there we go. Yes, yes.
We've taught this class how many times?
Well, the sad part is on test day, all they're going to see in their head is that messed up thumbs. Okay. So
How many times have we taught this and no one's pointed that out?
How many amperes are flowing through a circuit when the applied voltage is 12 and in DC and the load is 120 watts? Okay. Well, no. It is, but it isn't. Right, for purposes of the formula. And like I said, all I would do is, okay, what do I want? I want amps. What do I have? I have 12 volts, 12 watts. So I want amps. I've got 12 volts, 12 watts, and that's.
You can use a converter at home, a power supply at home, plug that into 110 and it produces 12 volt DC. But all of our radios, whether it's a handheld or a mobile or the desktop, are on DC voltage, the inside of the radio. So that's why all these they use DC. Using the equation, it doesn't matter if it's AC or DC voltage, you're still using the same principles to get you your answers. It's just, you have to know, are they DC volts? Because you're working a DC circuit. If it happened to be an AC circuit, you're going to do the same thing.
Yeah, they could totally do this question without DC and it would be the same. Okay, decibels, a logarithmic unit used to compare 2 values of power as a ratio. 2 main rules of thumb apply to using dB in expressing power comparisons. 1 doubling of power is a change of 3 decibels. This is important to know. So if I double the power once, I've increased the decibels by 3. A 10 times change of power is a change of 10 decibels. So what is the approximate amount of change measured in decibels of a power increase from 5 to 10? I've doubled it. So it's 3. I'm just making sure you guys had the information. So yeah, it would be 3 decibels. What's the amount of power change measured in decibels of a power increase from or decreased from 12 to 3? Okay, so what would it be? -6, because you're reducing it. So, but yes, it would be 6. And again, what they're showing you here is you applied rule number 1 twice, because you've got a double and then a double again. So correct. What is the approximate amount of change measured in decibels of the power increase from 20 to 200 watts? So we're going up by 10. Rule number 2. So what would that be? Okay, and what's the decibel increase? There you go. That's Ohms and Power's law. Yes. Oh yeah, there's all kinds of engineering charts for the obscure number, but with regards to ham radio, that's what's correct. That's what's most important. Yes. Well, and for the test, it'll be exactly that. It'll be exactly that. Do we understand Ohm's law, power law? And you know what's amperes. What is that? Is that power? Is it voltage? Is it resistance? Okay. So as long as we've got that, Ohm's law. So let me go back and we'll go over the definition. It's a logarithmic unit to compare 2 values as a power ratio. Sure. Trying to think of a good one.
The best one is our antennas. When you look for antennas, an antenna like this is a high gain 2.5 dB gain. This is where you get the dBs really into, is when you're working with antennas for a practical alternative application. That's what we really use the dB for, is when we're antennas gains.
Didn't we go over here?
Nope. Correct.
Can you give a good example?
Give a better
So
example.
another example, and he's exactly right. It's how we measure gain on antennas, and that's how you can say, you know, why is this antenna better than this antenna? Well, this has a 3 dB gain to it. And this one has a 5 dB gain to it. Okay, the 5 dB gain gives me more signal. It's actually on the receive side of it. I'll receive 5 dB better on the gain. So that's, which equates to the same thing as my transmit, but we all do on receive. The other side of this is on dB for our receive for our sound. So I can have a signal that's 3 dB gain. I've increased my signal by 3 dB. Well, how much power did it take to increase 3 dB? So that's how they measure that. It's really on the science side of the radio and that experimental side of the radio than on the operational side. But knowing that in order to get a change of power, a change of sound from 3 dB to a 5 dB or a 10 dB, you need to know how much power of an increase it is. So there's loss. Yeah. If you're going the other way, yeah. What's your loss on that? So it's really good to understand, why is it that I've lost 3 dB on my signal? Well, it's probably because you've lost power. So it's a diagnostic thing. I've lost power. I've lost 3 dB. I'm sorry? Correct. 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 So if I'm 50 miles away on 20 watts and I have my volume set at a level, and all of a sudden you hit me with 200 watts, it's going up by 10 dB, you're going to break my ears.
And the converse is true. It'll go down if all of a sudden he drops down from
100 watts to 50 watts.
Yeah.
The guy says, I'm half the power. Right. Exactly.
Yes.
Helps you diagnose what's wrong, or what do I need to better in my system to make my signal better.
Okay. Making electrical measurements. What are the basic instruments for measuring electricity? How do I make simple measurements? What precautions or problems may be encountered, and how do I convert those pesky math prefixes? What should I know about batteries? Remember batteries, the key to remember with batteries is their direct current goes one direction. This is just kind of a recap from the last one. It goes one direction. Your voltmeter is going to measure that current potential, which is the flow of the electrons through your wire. Current is the quantity of flow, how much is moving, measured in amperes, and it's measured with an ammeter, which is really cool because the meters tell you what they're measuring: voltmeter, ammeter, and ohm meter. Yeah, they're freebies. And those are going to be test questions. So that's kind of cool. How do you make simple measurements? A voltmeter connects in parallel with a circuit. In parallel, obviously, simple terms, parallel means moving along the same lines, so they're side by side. Here's an example. You have this thing. So in the water example, you've got your current moving this way. Well, if I want to measure that, I need to have the meter put in parallel, so it's coming up this way, going through the meter at the same time it's going through the pump, and it measures how much motion or how much current there is. Okay. Same thing with the electric current. It's going to be the exact same type of setup. And again, is this alternating current or direct current? Well, but which is this? Well, they're moving one direction. And then you have a battery here. Correct. So an ammeter connects in series with the circuit. And in series means it's part of the circuit. Okay. So you're going to basically make a little hole in that circuit and put your meter there, your gauge there, so to speak, and it's going to measure the current as it's part of the circuit. So it measures current or amps connected in series. So in the water example, as you can see, instead of having it come here and then your meter's up top, it's part of that circuit. Same thing with the current in the electricity. It's part of the circuit. And it measures the entire current. So everything that goes through that circuit, it's going through the meter as well as whatever component you have on it. Test questions for sure. When measuring high voltages, be sure the voltmeter leads are rated for what you're measuring. So I can't put a voltmeter that's rated at 12 volts in that wall. That's 110 volts. Yeah, it's bad juju. Yeah, just like that. And you get to pull out your wallet again and buy a new one. Yeah. Right. And
Yeah.
right.
There's one of them at Walmart that I use, and it's $13, and you can plug it into the wall, turn a switch, plug it into a battery. Same thing does both, and the leads are rated for the wall 110, so you don't get fireworks.
You can pretty much get these anywhere. You can get them at AutoZone. Problem with the ones that you get at AutoZone, because they're dealing with strictly car batteries, they're all going to be DC.
Yeah, the ones at Walmart are actually designed more for house stuff than designed for battery stuff. So they're a little bit better built for when you're working with a higher voltage. Like Dad was saying, you're not going to be using the fine detail ones unless you're building things, and that's when you want to get a strictly like 12 volt only one if you're going to be working with anything under the 12 volts. So just one from Walmart is pretty much all you're going to really need.
Most of the multimeters, well, all of the multimeters will measure pretty much all three of them, amps, ohms, and volts. So, but you can get strictly ohm meters, you can get strictly ammeters, and you can get strictly voltmeters. Well, yeah, absolutely, absolutely, absolutely. But what I'm getting at is you're going to measure, you're going to measure your ohms with an ohm meter, and it basically measures resistance by passing a small current, small known current through the resistor, measuring the voltage and calculating the resistance using Ohm's law. So here you have a resistor, and I can't read the bars on it to tell what it's rated at. They plug the leads onto it, and the multimeter or the ohm meter is going to run a current, small current through this, and it's going to tell what the resistance is as the current's coming back into the meter. Ensure the circuit is not powered when measuring resistances with an ohm meter. It's extremely important. Well, and I was going to say, and that's a paperweight, or actually goes in the trash because you'll melt the hell out of it.
Alligator tears will follow.
Yes, big ones, big ones. Or the circuit's current will interfere with the measurement using the meter's known current. Resistance measurement. Sometimes a capacitor is with stored charge will discharge through the ohm meter while measurements are being taken, even though the circuit is not externally powered. Capacitors hold a charge. They have a capacity, that's why they're called capacitors, so they hold a charge. If you're not careful and sometimes unexpectedly, they'll discharge through your meter.
Okay, I know this is probably going to date me a little bit more too. Who remembers those film cameras, disposable cameras you can get from the store way back when we had all those? Yeah. So, if you remember taking those apart and you got that flash and you took the bulb out,
Yeah.
you hit the charge button and you touch your skin with it, that discharge is the capacitor discharging the electricity into your skin. So
I think it's a safe bet. I think it's
you never did that?
I think
Oh
it's a
man, we
safe
made
bet,
homemade
Chris, that
tasers.
none of them did that.
We made homemade tasers and we ran around and had fun. You lit a tennis ball on fire.
There's two, because I would do that. I did do that. So if the ohm meter initially indicates low resistance and then shows an increasing resistance over time, the circuit probably has a large capacitor which is discharging. So if it reads the ohms and then all of a sudden it's going up, you've probably got a capacitor that's discharging. And that little diagram gives you kind of an example of how that works. Yeah. Yep. Exactly. Okay. A multimeter is commonly used to make measurements of voltage and resistance and amps. Caution: if you attempt to measure a voltage when using the resistance setting, the multimeter may get damaged, because remember, with the ohm meter, it's using a current, so it's actually providing its own small amount of current. So you could actually damage your multimeter. So, do you remember going from, you covered that last week, right? Going from high to low, low to high. This is what helped me, so I hope it helps you guys. Those are the 6 or 7 most common that you'll use with regards to ham radio. Mega, giga, and kilo, and then on the smaller end, milli, micro, nano, and pico. And the way I remembered it is the 1 goes on the 3rd, 6th, 9th, or 12th digit past the decimal point. So if it's micro, I have a decimal point and I have 5 zeros with a 1. So the 1 goes on the last digit. Everybody good with that? Any questions on that? Okay. I didn't hear you say again. Yes, yes. Well, so if I have kilo, yes, that's your base number. So if I have kilograms, if I have 1 kilogram, I have 1,000 grams. So there's your kilo. Okay, your 1 is your base. So if I have a megagram, I have 1 million grams. So this would be 1,000,000 ones, basically. And then the same thing with nano, pico, micro, milli. It'd be less than 1, but it'd be a fraction thereof. Make sense? Okay. And then here we go. And those will be on the test. So how do I convert, how many milliamps is 1.5 amps? So which way am I going to get milli? To the right? Well, if I have 1.5 amps, that's my base, and I want milliamps, which way am I moving the decimal point? To the right. How many times? So I go 1, 2, 3. Okay, so okay, you're right. 1, 2, 3. So I put a 0 in those places. Yep. Nope. Yep. Microfarads. And again, when I did this on the test, I took out the farads. I don't care about farads. I just need to know if I'm going from micro to pico. So if I have, how many microfarads are in 1,000,000 picofarads? Which is the bigger number? Okay. So is pico bigger than micro? Okay, so which is the bigger number? Right. But my bigger unit, let's put it that way, my bigger unit is micro. It is bigger than pico. So if I have 1,000,000 pico, how many microfarads do I have? Okay. Is it 6? 1, 2, 3, 4, 5, 6. So we should have 1. There we go. 1 micro. If an ammeter calibrated in amperes is used to measure 3,000 milliampere current, what would the reading show? How many? 3? Okay. Right. Correct. So there's
Here,
several.
before we get on to batteries, does that make sense for the movement on the decimal point? Okay, this is the one. Yeah. This is the one. This section is the one that most people have the problems with. Is converting.
That's opposite. Oh, I see what you're saying. Okay.
Yeah.
I see what you're saying. The reason why I did this is because all of these are smaller than 1. Right.
Yeah.
Right.
You did the real way of doing it. They went the reverse way. Yep.
And that's typically what I do on paper, is I put kind of like the old XYZ graph, have the 0, and I go both directions. So my -1, or you know what I'm saying. So I'm with you. I'm with you.
We're getting this one. Okay, cool. Yes.
Right. Right.
Yes. Everything's in multiples of 3 here.
And you do. I mean, it's not part of any of this, but we do realize there's ones in between here, several. But this is what pertains to ham radio. Right.
Especially when they drop off my check.
Oh yeah. Yeah. Who's FICA? So we have multiple different types of batteries, way more than they list here. There's tons of different types of batteries. You have carbon zinc, and which is basically alkaline batteries. They're non-rechargeable. It's the ones it's the Duracell D cells, C cells, all those, they're non-rechargeable. You have the nickel metal hydride and nickel cadmium, which are rechargeable. The NiMH is nickel metal hydride, and NiCad is the nickel cadmium. And again, these are batteries, so they're typically 1.5, 3, 6, 9, 12 volt style. Then you have, yeah, all DC. Anytime you refer to a battery, it's DC. Anytime you refer to a battery, it's DC. It's the old carbon zinc, yep. Well, and the lead acid are rechargeable to a point, but we won't get into it.
The carbon zinc are the ones you go to Walmart and you just buy a pack of AA's. When they're dead, you throw them away.
Yeah.
That's what those are, just carbon zincs. Yes, all your remotes and everything. Yeah.
Yeah.
Yes,
Exactly.
'tis the season.
I just had to buy a box of 24.
Yeah.
Lithium ion, they're rechargeable. They have a high energy density, long life for mass per weight, becoming very popular in these radios. In fact, the other radio that I just ordered uses the lithium ion. And a lot of them will actually look like C and D cells, but they're the lithium ion batteries. Lead acid, it's rechargeable. It's older. It's car batteries. It's the old technology. A lot of the newer versions of these have the gel cells. Motorcycle batteries are notorious for the gel cells. High surge currents for radio transmission needs, and they're still widely used. Let's see, maybe recharged by connecting in parallel to a vehicle battery and running the engine carefully. You ever done that? Have you? To run your radio? Cool. Slave cable attachment? Sweet.
I've got a lead that comes off the positive close, lead comes off the negative close. There's a plug on my bumper. Plug that in. I'll get it fixed to the battery that I want to charge. I'm running my truck at the same time. Truck battery and my
You ever jump
When
a car?
you-
You ever seen somebody jump a car? Yeah.
That's parallel,
They're putting
yes.
the second car in parallel.
Yep.
Yeah. The
Yeah.
second car is parallel to the first car.
Instead of having a second car, you have a second battery that you're actually charging.
Right. Yeah, he's all high-fangled like that.
When I had my Jeep, I had a second battery in the back with a solar panel that always kept it charged. Because I had a tendency of leaving stuff on. I had a switch that I had that would actually physically connect the batteries together. I'd jumpstart my own car. I had to wire everything up in parallel because if not, then it would drain my other battery as well as the one that's in the car. It was kind of fun when people were like, oh, you need a jump? Nope, I'm good.
That's chapter 8 in a nutshell. Are there seriously any questions with Ohm's law, power law, amps, ohms, volts, parallel, series, all that stuff? Is there any questions? We got it? Because you will see a lot of that on the test. Right. Well, and here's what helped me just before the test was I went home, kind of reviewed all of our stuff, and I in my own head, I thought of ways that I could make it, one, make sense, and two, easier to remember. So, like with me on this, the way I looked at it was kind of like what Chris was saying. When you multiply, they're side by side. When you divide, you've got one above the other one. And it's already designed that way with the way this is set up. So it made it easier for me to remember how to work that. So I just kind of found ways that made the different components of the book and the knowledge make sense, and how it was easier to remember. Because obviously we can't have our books at the test. Right. Right. Well, and like with With the decibel part, because it deals a lot with antennas, he's really good, and he makes it make more sense for me because I've never dealt with the antenna side of it and how to troubleshoot it and understand how the decibels come into play with that. The slingy? Yeah. Right.
That's the hardest thing about electricity because 90% of it's theory. You happy now? Once you visualize, and that's why we use water to comparison, because you can see water, but you can't see electricity. So that makes it hard. Now, I'll give you a little side story here. I was a journeyman electrician. Worked myself through high school as a journeyman electrician. Learned a lot about electricity stuff. The whole Ohm's law and the power law stuff. I learned the formulas. Drove me batty. Fast forward a number of years. I'm not going to say the number, but a few years ago when I found this book and Stu's way of covering the number, if I would have known that 30 years ago, I probably would have stayed as an electrician because that made that math part of it so much easier because I always got my equations backwards. I was always doing it the wrong way. I was trying to find the wrong, I was using the equation backwards and found my wrong answer. It just never made sense to me. When I saw that, it all clicked. It was just the easiest thing in the world because I couldn't visualize how to make that formula work. It was really hard for me. So something that easy, light bulb for me.
Well, and one of the things that helped me remember how to set these up so I didn't have IER or any of that, this is alphabetical if you go counterclockwise. Alphabetical. And this spells pi if you go counterclockwise. So that's how I remembered it. Because otherwise, because my whole concern was, what if I put these backwards or I put these backwards? So if I did it, if I create a way of memorizing it, it made it easier for me. So it's alphabetical going counterclockwise and pi going counterclockwise. Right.
Okay, so nice. This is a lot to take in. We're going to go ahead and jump out for 10 minutes. So we'll be back here on the hour. We are back on time, so we're good to go with that. The next section is the Hamtronics, which is the most fun out of all of it. Did anyone want to go out and see that SWR example that Dad was talking about with the antenna out in the truck today? Can you see the antenna move and everything? You want to do that? Okay, we'll do that right now for 10 minutes. If everyone wants to go out there, we'll all do that. And we'll come back at 8 o'clock on the dot. Okay, so yes, we did go a little over for that example, but I think it was worth it for the people that went out there. You guys got a little more hands-on, figured out how it works. So now we're gonna get into the fun stuff. This is the Hamtronics. It's, well, yeah, you guys gotta wait till next week when we do space contacts. By the way, for anyone who didn't know, tonight is the Orionid's meteor shower. Orionids. It's always so hard to say that one. So when you guys are leaving tonight, look for Orion and Orion's belt. Look further up the sky than Orion's belt, and that's where that meteor shower is going to be. It's the third brightest meteor shower of the year.
That's probably why I had all that weird noise on 40 meters.
Yes.
I forgot about the meters.
Yep. And there is people right now.
Are people.
There are people. It's the second time that fell. There are people that are on the radios right now, spinning through the bands, trying to hear each of them crashing into the atmosphere and counting them. There's a full contest going on tonight, and I think the guy in Tucson
Holds the record.
holds the record for the last 3 years on this particular meteor shower. Huh?
Manually
For counting manual, yeah.
Yep.
You'll hear a every time it hits. You'll hear a different sound. Yeah, he records them. Yeah. Yeah. Actually, I think one year Guinness Book of World Records went down and sent a guy that actually sat there for the whole 14 hours that he did this whole count thing and just sat there, and every time that the guy would say, yep, 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 he hit the little button, and that's how they did it. It was kind of cool. We'll turn it over to Hamtronics. We'll talk about space contacts next week.
Okay, so Hamtronics is basically taking the stuff that we've already been talking about and how it was applied to the ham radio. This is a photograph of a circuit board from a typical radio setup. So we're going to talk about some of these components that you see on the circuit board. You have integrated circuits, we have capacitors, we have RF chokes, we have some resistors in here, a lot of integrated circuits. So we're going to talk about how this integrated circuit has all these big components pressed inside the small thing, and how that little tiny radio, wherever the heck that went, the little tiny handheld can work. That's a lot. Okay, what do those electronic components do, and what symbols represent the electronic components? So an integrated circuit, or an IC, combines several semiconductors and other components into one package. That's really the simple thing. ICs are the things that changed our world from transistors into IC circuits and made everything small and compact and the world that we have today. So all you have is just the different sizes of ICs components is how many semiconductors or components that they've packed into these things. They build them up on layers, compressed them. Intel's really done a heck of a job doing this. So semiconductors, one of several types of materials with electrical conductivity between that of a conductor and an insulator. Electronic components, including ICs, this is an IC, an integrated circuit, resistors, capacitors, inductors, transistors, and diodes. And others manipulate electricity to control the voltage currents and AC phase relationships and digital pulses in the performance of tasks and computations. All that to say, all these little components make our radio work. It makes the magic. So the schematic symbols, the standardized representation of components in an electrical wire drawing. Back in my high school days, I actually had ambitions of being a draftsman, and I learned all this stuff in high school in drafting, and it was one of the things I was going to do. So it was lots of fun. So we want to know, why is this a diode? Why is this a resistor? Why is this an IC circuit? How do I know this? By looking at the diagrams, we're going to break this down a little bit. So each symbol represents an electrical component. If you're going to get into the electronics part of it and troubleshoot your radio, this is going to be really important. If you're not going to do any of this, this is going to be really important to pass the test. That's kind of the difference in your life. Okay? All right, so important for one day, exactly. So my capacitor shows my plate and my reflector on my capacitor. This is my symbol for that. This is my symbol for my resistor. It tells me the resistor number, which is R5, R meaning resistor. And on my schematic drawing, it'll say what an R5 is. And it's a 1000 ohm resistor. That's what the 1K stands for. I know that because I studied this crap. IC circuit, that's that integrated circuit. So I could have a bunch of resistors and capacitors all crammed into this IC circuit. It just makes things smaller. The diagram accurately represents only the way components are interconnected. If you lay this diagram next to the printed circuit board, they will not look the same. Don't lay this and say that little thing kind of lines up to this drawing. It must be a diode. Not going to be the same. This just shows how they are connected electrically. That's all a schematic is. You still got to go find out the component. The nice thing is, like this R5 on the printed circuit board, it'll have R5 printed on the board, and you could find that component number. The C5 is a capacitor. You could find that component on the board, but that's the only way that you could match those things is by that landmark. Little side note, you don't need to know that for the test. All right, resistor opposes the flow of current in a DC circuit. So your resistor's diagram is this sharp pointed squiggly line. And these are the different resistors you can have. There's a whole variation of different resistors. This one that looks like a potentiometer it's a variable resistor. So I can adjust value that resistor will work on. And these are really big ones. Remember that antenna tuner that we're talking about? Those 3 knobs that I said you adjust? They're 3 big butt resistors. That's what it is. That's what they are. So you're adjusting the value of those resistors to make that antenna match your. That's all you're doing. You're putting three resistors in series, and you adjust their value to make it work.
Also, along that line, if I may, I'm sure you've all seen dimmer switches on lights. It's a variable resistor. Instead of having an on-off and you got the variable where you can dim the lights, it's a variable resistor.
That's all it is. So these resistors are fixed values. The little painted stripes that you see on these things, there's a little chart that I used to carry when I was an electrician that I could turn little wheels to line up these colors the same way that's on my resistor, and it would tell me the value of the resistor. So that's the significance of the colors on this thing. It's kind of side stuff. You don't need to have that for the test, but it'll win you a beer if you bet somebody on how you know how to read a resistor. So potentiometer, aka a variable resistor, that's this little guy right here, controls the resistance, and it's often used as an adjustable volume control. So our volume control is just a variable. The knobs on my antenna tuner are adjustable resistors. So your variable resistor is the same diagram as a resistor, but it has this little line with arrow on it. That arrow signifies that little paddle that's on the variable knob. So as you move this arrow up and down your resistor, it changes the value. That's how you know this is a variable resistor. This is a fixed resistor. So this fixed resistor is looking for something like this or one of these guys. This variable looks for one of these guys. Make sense? Okay. Always. Uh-huh.
The schematic is showing every.
It's a flat drawing. It's a flat drawing.
It's just flat. It's not 3-dimensional. Correct.
Right.
Correct.
Right. Chris, I pressed something that made this thing freeze. Oh, I know what I did. Never mind. Here we go. Okay.
But
Yeah, it's just a flat drawing of how the components are related to one another.
And keep in mind, the components themselves on the actual device can be stacked. But the drawing is going to have all the components in one-dimensional drawing. Yes.
Yeah. Yeah. So a capacitor stores energy in an electrical field. You guys all know what a taser is? They're a lot of fun. Yeah. A taser gets its energy from from a whole bunch of capacitors stacked together. So it's got four batteries that charge the capacitors, amplifies that electricity, holds that in the capacitors, and when it's discharged, that's where you get the 50,000 volts from 4 batteries, because they're capacitors. Yep, kind of like that. Yep. So a capacitor, again, this is our drawing. It's one straight line and one curved line with your leads that come in, and your electrical charge is stored in the middle. That's a capacitor. And capacitors can either be a can looking or a little flat wafer type looking thing. If you lightning damage is great. Finding lightning damage in a radio isn't a great thing, but to find one of these things, we'll say in the field, I blew a capacitor. Well, one of these things actually blew up. You can get an electrical discharge from lightning, usually from lightning. It doesn't take a direct hit either. You can get what we call static discharge from lightning off of your antenna. These capacitors don't like that, and they'll catastrophically fail. If you're around when these things blow, it sounds like a firecracker going off. There's a lot of energy that's displaced. Even these little things, and they're, I mean, this big. They're not that big. It's inside your radio. Horrible noise. Yep, she be done. So 2 or more conductive surfaces separated by an insulator. There's a insulator, physical insulator inside here. Could be paper, could be ceramic, could be a couple other different materials in there, but you have some type of an insulator in there. And the capacitance is the ability to store energy in an electric field in units of farads. We measure our capacitor in farads. That's our base measurement. So an inductor, usually a coil of wire, it stores energy in a magnetic field. This is our inductor. So I've got a magnetic field, so we've got copper wires that are wound. That's what this is representing, is the windings of copper wires. So here's my inductor, here's a smaller one, and here's a ceramic sealed one. So this is wrapped up in this little tiny inductor. Okay, that's all we need to understand about that. Variable inductors, again, we have that line with the arrow on it. We have variable inductors. It all depends on what we're doing with our energy, on how we want to either amplify it or increase or decrease the energy in the circuit. We have a variable inductor. So inductance is the ability to store energy in a magnetic field in units of Henry. We measure inductance in units of Henry. There's our magnetic field, what it's doing. A diode, this is a different component. A diode allows current to flow in only one direction. Where the arrow is pointing is where it allows electricity to flow to. So you can have power that flows this way, but it won't flow this way. Diodes are really important when you're building circuits. Like we said earlier, if I have a battery and I have a fan, and my positive on the positive of the battery, negative on the negative of the battery, my fan goes clockwise, which is the way I want it to go, and blows air on me. If I switch the lead, the fan goes the other way. Well, it doesn't help me at all. It's going the other way. If you put a battery in your radio backwards, you're sending electricity backwards. A diode prevents that from happening. So they put a diode in the beginning of the circuit, so if the battery goes backwards, it doesn't let the electricity go this way, saves your radio. It doesn't work. Flip it around and right, and it's a safety net. Yes, ma'am. In your house, the ceiling fans in your house, yes. What it is you have in a fan in the house, because it's AC, you have 2 sets of windings. So you have one set of windings to make it go clockwise, one set to go counterclockwise. When you flip that switch, you're actually moving the contact for the power from the left winding to the right winding, and that's what makes it reverse. In DC, all I got to do is change the power. The blower fan in your heater in your car, if I would turn the power leads around on that blower fan, it'll suck air out of the cabin instead of blow air into the cabin. But that's all I have to do. I don't have to do anything to the motor. In an AC fan, we actually have a different set of windings. Yes, it prevents the flow of electricity, or it allows the flow of electricity in one direction only. So in an AC circuit, you're only using half of it. I can really get into the electronics on this one. I don't want to, but just understand that a diode only allows the power to go in one direction. For our radios, it's a safety. Energize the circuit the wrong way and burn things up. That's a good way of remembering it. But a diode only lets you power go in one way. So these are different diodes. Where this band is on the diode, that tells me where the power is going through. So it's going through this way because the band's on this side of the diode. If the band was on this side of the diode, the power would be going this way. Just one of those little side notes that I know from these things. So 2 electric leads, 1 anode and 1 cathode. These are what we call, the anode is on one side of the anode is on this side of the diode, and the cathode is on this side of the diode. So just know those terms when I'm actually connecting a circuit. The directions, if I'm going step by step on the directions, it'll say the anode of the diode goes on this terminal. That's how I know which side which way my diode is supposed to go into the circuit. So the cathode usually identified with the white stripe. So cathode, where that line is where that stripe is. So my power's going this way. It's going this way. Power's going this way. Make sense? Okay. Oh, that's a good way. There you go. Okay. An LED, a light emitting diode. We've seen a lot of those things here in recently. A lot of TVs now are LED televisions. They're light emitting diodes. There's thousands of diodes in this screen that emit light to make a picture for us. So this light emitting diode looks just like a diode, but it has these little lightning symbols off the top of it. That's a light emitting diode. On my radio, we have red, yellow, green diodes that are set up. That's all it is. It's like a light bulb, but it's a light emitting diode. The nice thing about LED lights, they take a fraction of the power to emit light. So they're very power efficient. That's why we have those LED flashlights, and you can have that big head on that flashlight and have those little AAA batteries that run it, and you can really get a lot of light because a high efficiency light that comes out of those things. Okay, so this is all of those symbols that we just went through one at a time in one chart. Resistor, resists measured in ohms, functions that opposes the flow of electricity. This is what these look like. An adjustable resistor, capacitor. Here's an adjustable capacitor that has the line with the arrow through it. An inductor, adjustable inductor, a diode, and a light emitting diode. You can have 2 different types, either the solid line with the arrow or the lightning bolt line with the arrow. Either one of those are a light emitting diode or an LED. Okay? Yep. Yep. Whatever they clicked on the icon, that's the one that got dropped in, but they both mean the same. Any questions on components? Yes. Yep. Go back to this.
It's capacitance, right? It's the how much is stored? Electricity.
How much
How much
the electric field? The electric field.
How much is being stored?
Is stored in. We measure that in farads. Well, depending on the size of the thing. I used to work on motors that were, when I was an electrician, I lived in Iowa, so we did have a lot of grain bins and those big blowers that they used to pull the silage up the silo to fill the silo. Motors, huge. I mean, the motor itself was this big. The capacity, like that big around and that long. Don't touch the conductors because we stuck a screwdriver in short. I burned up a lot of volts that come up. So the ones that we deal with radios, yes, they're very small, but they can be as big. It all depends on being applied. Does that help? Okay. All right, so transistors. What's a transistor? What does it do? Symbols, common combinations of electronic components, and how can I put all these components together? Very carefully. So a transistor, class of electronic components capable of using a voltage or current signal to control current flow. What's the first most popular use of a transistor in public use? Transistor radio changed the world when we had transistor radios. So the transistor symbol, we have a BJT and an FET. This is a circle with our transistor and a diode inside that transistor. So it only allows power to go through one direction into that transistor. We're going to go through these really quick because I don't want to get into deep electrical theory on this. We could go crazy with it, but I don't want to swamp your boat, but have enough that you can understand it and work for the test. So I'm not going to get into different components of it. Transistor usually made 3 layers of semiconductor material. I did that again. I did. A transistor can be used as an electronic switch or a signal amplifier. The transistor's ability to amplify a signal is called gain. So depending on the gain is how heavy of a switch it is. So with collector or your source, it's your base or your gate. Your base is what we call the component. The gate is what it's really doing. It's controlling the amount of flow of electricity that's going through my wire, and the emitter or down to the drain. So how much is it draining off? So a bipolar junction transistor, a BJT, has a PNP or an NPNT type. There's a lot of verbiage in here, so bear with me on this. Field effect transistor, FET, field effect transistor, those are the 2 different types that we have. So my signal, the signal that I put into this transistor, is how I adjust it. That's how I adjust the gate. That makes the gain. It lets more or less electricity go through it. Oops. And what's left goes down the drain. All I'm doing is adjusting the amount of electricity that's going through my circuit to make it do the job that I want it to do. There's 100 different things that it does. Basically, for us in radio, it allows us to hear different radio frequencies. That's basically what you're doing. So bipolar junction BJT has your base, emitter, and your collector. Okay, remember what I said back here, your base, your collector, your emitter. Your emitter is where your drain is, the collector is the source, and the base is where I'm adjusting it. So my collector is my source, my emitter is my drain. That's why it has a diode in it, so that it doesn't go back into the transistor. And my base is allowing me to adjust how much electricity goes through it. That makes sense? They're kind of complicated, and there's a lot of schools on these things, but just understand the basic components of it. So a current applied to the base, put power into the base, controls a large current flow from the collector or emitter. I can have, I'll just have 100 volts come in here. I can have 10 volts come in here. The 10 volts is adjusting this to make that 100 volts down to what I want it to be. Maybe I want 12 volts. Okay. So a voltage applied to the gate controls a large current of flow from the source to the drain. So as I put power into here, and again, there's that diode to keep the power from going the wrong way. That allows my my flow from my source to go to the drain. So my control power, how much control power I'm putting in here, adjusts my valve to allow this power to go through at a controlled rate. That's all we're doing. And these things have different looks to those. A lot of information for like 2 questions, I think, on capacitors. So hung up on the capacitors. A lamp and light. Any lamp that's in there has this, or sometimes you'll see this as a little squiggly, like the filament in regular, the old incandescent bulbs. But this is your lamp. Your battery.
Real quick on that lamp, that it's any light except for a light emitting diode.
Except for an LED. Yep.
Because
So that's an incandescent lamp.
Yep. Because on the test question, I read it through. It'll say, what is a symbol? And it'll say light, LED, all that stuff. So just know lamp means anything but a light emitting diode, LED.
And your battery symbol, antenna is your triangle, and a fuse. Real important, know where your fuses are on your radio, because when you burn one of those things out and the radio doesn't work, you get really, really mad and you forget to check your fuse. Check your fuses. Real simple fix. So what those symbols are. Transformer. Transformer is commonly used to change 120 volts AC, which is house current, to a lower AC voltages or other use. So that little power supply that that's okay. The power supplies that we plug into the wall to charge our cell phones is a transformer. Yeah, we all know what those things are. Yeah, that's all it is a transformer. So it's a big bunch of copper wire wrapped around, changes the power from 110 to it actually has an inverter in it too, so it changes it from 110 AC down to 12 volt DC, so that it'll charge that battery that actually runs on AC.
Yeah, this doesn't like 110 volts.
Yeah. Okay, so then we have a meter. So your display signal strength on a numeric scale. A voltmeter or an amp meter. Pretty easy. The V for volt, A for amp. But that's where your meter would be in your circuit. You want to know what those symbols are. So you have a voltmeter and you have an amp meter. Okay. Switches. My favorite. I love switches. Switches are just disconnects in a circuit. It's either on or it's off. That's a single pole switch, double pole, double throw. Single pole, single throw. It's just an on-off switch, just like that switch on the wall. If I was doing a diagram, that's all that is. Double pole, single throw. So I have a switch, my little tab that I hold on to. I can either switch it up to turn on one thing, switch it down. It turns off the first thing, but turns on the second thing. That's a double pole. So a pole is I'm running something with it. Double pole, double throw. I have one switch. I have two sets. Well, 2 sets of contacts. On things. If I turn it down, turns off those 2 things on 2 entirely different things. That's what a double switch does.
You ever seen
Multiple
Frankenstein? That knife switch he throws, it's got 2 contacts on both of those blades that come down.
Movie trivia. Double pole, double throw. What the hell? I'll be throwing popcorn at her now.
Right.
Yeah. So a relay switch is controlled by electromagnetic. A relay switch is, and you have these in your car. When you turn on your car and you hear that click, but it doesn't do anything, you're turning on a relay. That relay is taking a little bit of power from your ignition. On the battery, those big cables that run the starter, those cables don't go up. is turning on a relay switch, turning on an electromagnetic coil right here that sucks in this little lever that turns my switch from off to on. So when I turn on my ignition, I'm putting 12 volts with a little bit of current, with a little bit of amperage to it, to this coil to turn on my switch that has all that amperage to start my engine. That's what you're hitting that coil that turns that on, so I can control a little bit of electricity to run a lot of electricity. Does that make sense? So that's a relay switch, and those are remotely done. So this is in its off position, this is in its on position. Then when the switch is turned off, the spring pulls that lever back to its off position, because the electromagnetic coil doesn't magnetically move that switch over. And they look like this. This is actually what you see in your car. They're fun to play with. I build all kinds of projects with relays and stuff, and yeah, I can get into all kinds of crap. Puts it on an auxiliary battery. So when he turns it off, the relay turns off. It goes to his auxiliary battery. He can still play on radio, but he still has his engine battery in his car. That's what he's using there. All right. So a regulator is a circuit that controls the amount of voltage from a power supply. If we have, for instance, the power that comes out of the wall here at the house or in your house, if you put a meter on it, it could be anywhere from 110 volts AC to 125 volts AC. Depends on the day, depends on the generator, depends on lots of things on how much power comes out of there. Some of our sensitive electronic components don't like variations in power like that. So a power regulator takes in that power that is coming in, whether it's 125, it doesn't matter, through capacitors and a bunch of other components that are in there. It regulates the power and puts it out at a constant power. So I can bring in 110 volts AC, convert it to 12 volt DC, and it regulates that. It's always at 12 volt DC. On your when I have that off, and I can show you on the voltmeter out there too. When I have the car off, I put my voltmeter on the battery. It shows 12 volts DC. When I turn on the engine and the engine starts, there's an alternator that charges my battery. Now my battery reads 14.3 volts DC. My radio doesn't like 14 volts DC. It likes 12 volts DC. That 2 volts is a big deal to sensitive equipment. So there's voltage regulators that are built into those mobile radios. So that when it gets 14 volts coming in, it holds back through resistors, holds back that extra voltage, bleeds that off, and only lets the radio see 12 volts. It's a constant power supply. So that's why when you turn off the car and the radio's still going for just a little bit and then it kind of dims out, it's the power in that regulator, that built-in power supply in that regulator, power from the capacitors in the storage. Slowly, the light slowly dims. That's why it's doing that. So when you turn off the switch, it doesn't just turn off. You've got a voltage regulator in there. Does that make sense? There's some things that you're seeing. Oh, now I know why this is doing this. That's why. Okay. So a rectifier, a device or circuit that changes an alternating current into a direct current signal. So a rectifier takes your power, goes through diodes, takes your AC power, and converts it into DC, which what, whoop, went too far, which is what your, and he just took it, the charger that he had takes it from the AC into DC, so it charges that DC battery. So you have a transformer. This is a transformer because this computer runs on AC power. That's why that's a transformer. It's transforming it from 120 volts AC to, what did you say, 9 volts AC? 19 volts AC. You have a rectifier, that's that box that's plugged into the wall, plugs into his charging unit that charges his DC battery, or my cell phone, that little cube that I pull into the wall, thank you, Apple, that plugs into my USB port. It's a rectifier that takes the AC current, turns it into DC, and charges my DC battery. Because you can't take AC and charge a DC battery with it. It has to be the same type of voltage. What, Chris?
Now, we're talking about how batteries are always DC. Laptops have batteries in it. All we see on the outside is the transformer box going into the computer. However, right next to the battery, which is if you put your hand right next to the battery when it's dead and it's charging, there is a rectifier built into the computer, taking that same voltage that is coming into the computer for it to run and turning it into DC power to charge that battery.
And that's where they get hot.
Yep.
Because you're bleeding off that electricity. Because electricity is doing this. So the rectifier takes half that signal away. It's only taking the one way.
Mm-hmm. Yes. It's cool to touch. Exactly, because it's no longer using the rectifier. Yeah,
things are making sense. Amazing. It's amazing what you learn in amateur radio class. Stuff that's near and dear to your life. All right. Yeah, no kidding. Tune circuits. Connected in series or parallel, an inductor and capacitor can form a filter or a simple tuned or resonant circuit. What the heck is all that? This. All right, so my antenna, my inductor. This is a what kind of capacitor? Why is it a variable capacitor? With an arrow. With an arrow. That arrow is very important. Don't cheat me out of an arrow now. This is a symbol we haven't talked about, but this is called a ground. Okay? So this is my ground or my negative. Next slide here. So the tuned circuit allows current to flow very efficiently back and forth between the inductor and a capacitor, alternatively storing and releasing energy as a magnetic field inductor and an electric field or capacitor. So my power is going back and forth through here. That's what my tuned circuit's doing. There's my positive, my negative. My inductor's letting it go. Positive and negative. Negative and positive. Okay, so it's flowing back and forth through here. The values of capacitance and inductance may be selected so that a current So we've taken, in our radio, we have DC power and we have AC power inside our radio. It's dependent on what we're trying to make it do. So just because it's connected to a battery doesn't mean everything in that radio is DC. There's some things, very small things, that we're creating AC electricity for to make it work. Okay? I just thought these things were just magic. There's actually science to them. All right, so a control circuit used to control a lamp, motor, or other device. This example is pool figure T1. These are always fun. In our extra tests, there's a lot of these things that drive you nuts. So you'll get this drawing, and if you're lucky enough to get this in Technician, there are things. You'll see this drawing in there, and it'll say, what is component number 3? So it's a lamp, okay? What's component number 4? I've heard 2 different things. Which is it? It's a battery. Okay. Component number 2? Capacitor. Component number 1? Resistor. Component number 5? That's your ground. Yep. So all these go to ground. So that's your drain. Because remember this, your capacitor has a drain. It's going to ground. If it asks you if it's the bipolar thing or the other one, which I can never remember, I have such a hard time remembering those things. I don't think it asks for the different
It does not ask for which type it is. It just on one of your questions.
components. Yeah. Yeah.
Yeah.
Is it a capacitor?
Now, why don't we
Well,
step?
let's see.
Why don't we?
Number one's a resistor.
Mhm.
So we got that. Number two is a transistor.
So
What did
there
I
you
call
go.
it? I called it a capacitor. Didn't
You
I?
called it a
I was
capacitor.
wrong. Transistor. I was wrong. I'm tired. I'm sorry. Yeah,
And you
it's a
want to test
transistor.
for your extra class?
This is why we have the answers. So this is the bipolar junctional transistor. That's the 3 of them. Yes. Yep. 3 was the lamp. 4 was the battery. All right.
Okay, real quick too. Every exam has this diagram printed on it. It may ask for a component.
It may not.
I got one of them when I did my technician test. This was on there, and I was all excited because I knew all the different types. Went through all 35 questions. Not one of them asked me for that. So
Disappointing.
just keep in mind, if it comes up, it doesn't mean you're gonna get the question for the figure.
So number 5 is the ground, which we already talked about. Okay. Signal goes in. Does the voodoo that it does. Lights up the light from the battery. That's our circuit. All right. Transistor functions to control the flow of current through the lamp. This transistor will make this light bright or dim. It allows how much electricity goes through there. So that's in this particular circuit, the amount of signal that comes in makes that light go dim or bright. You've seen on signal meters where seeing it on radios, the brighter the light, the more sound that's coming out of the speaker. That's what's doing that. The amount of signal that's coming in is opening this gate, letting more power go through, making that light brighter. When the signal gets really low, the gate closes down, lets less power go through, and the light's dimmer.
Dimmer switch in your house.
Well, yes, but no. Yeah, that's a better one than the dimmer switch. Yeah, because that's a different thing. Did I? Oh, okay. It's just doing that again. Okay. Soldering, one of my most favorite fun things to do. I really
Warning: soldering will smell.
Yeah, don't breathe the smoke. But it's a lot of fun. So solder is a blend of metals that melt at a relatively low temperature. Relatively. Don't touch the soldering iron; it'd be hot. It'll burn you. But it's rosin core solder is best for radio and electronic use. You really know this because I haven't seen a technician test yet that doesn't have that question on it. Rosin core solder is best for radio and electronic use, as it contains rosin to spread around solder joint and help reduce oxidation. Solder, this little coil right here, and this little stick of wire that this person is holding, this is called solder. If you got a magnifying glass out and looked at the end of the solder, you would see there's a hole in the middle of this, what looks like a solid piece of wire. Inside that hole is rosin. It's a gel liquid stuff. And when you heat it up, it liquefies, it melts. And it will turn your solder kind of an orange. But that rosin lets it stick to the other wires. Without that rosin, the solder won't stick right, and you get what we call a cold solder joint, where it turns kind of a molten color, and electricity won't go through it. So that's a big thing. So you want rosin core solder is best for electronics. The solder that we use for copper piping for plumbing doesn't have rosin inside it. You have to paint that little putty stuff on it. That's the rosin. So you melt that, watch it bubble, then stick the solder. And if you go too far and you put your solder out on that copper pipe where there's no rosin, it sticks to it. You can't get it off. That's why. So that's what the rosin's doing. Okay? All right, so cold solder joint, which I just talked about, is a grainy or dull surface appearance. All these solder joints are nice and shiny. Those are nice, properly done solder joints. If you get dull, dingy look to it, cold solder joint. You're going to have nothing but problems with it. It doesn't conduct electricity properly. Every time I help somebody or teach somebody to a connector on the end of a coax, we solder that center connector, that center conductor into the center point of the connector. And if it's a dull solder joint, it's a cold joint. Electricity, the RF doesn't go through it right. You'll have nothing but problems. You get a nice shiny solder joint to it, perfect every time, all time. So it's a little bit of practice on soldering. Questions, comments about solder? Cool. Sweet.
Like I said, we're back on time. Thank goodness. Yeah.
They're not. Basic components. Yep. Yep. And it's one of those things you either know it or you don't. But yeah, they're pretty straightforward. All right.
Now it's my turn. Guess what? You guys made it through day 3. We're still here. Look at that. So the quick question is, how's it going? I saw a lot of oh moments out there. Am I right? Everyone had at least one, right? A couple of you had a lot, which is good. This is why we're here. The more oh moments you have, the more things you're going to be able to remember on the test. All right. Back to the course outline. Before we get to questions, your guys' homework. Has everybody been following the homework checklist sheet that I have on here for you guys? No? Uh-oh. Yeah. Okay, so for next week, we are going to finish the book. So read chapters 10 through 13 to finish the whole book. And you're going to be taking those practice tests for chapters 1 through 9. Now, on here it says bring an object that uses RF. What did we learn? What does RF mean? Radio frequency. So anything that you guys have that has a radio frequency, bring that object in because we've got a really cool activity that we're going to do next week with them. Our activity today was getting to look at all the antennas. So don't cheat. Don't bring a cell phone in. Don't cheat. It does, but don't bring a cell phone in. That's cheating. Yes, he's going to bring the radio. We use wireless. No. That. Yeah. Bring in something that has an RF. So if it's just a receiver, yes. If it's just a transmitter, yes. I'll give you, for instance, we have remote controlled cars. Those are RFs. Just to give you an idea on that. Yep. Just don't bring in your ceiling fan. Yep, this is part of that. Look at the stuff in your house. Okay. Why? Shall I tell her the story of the guy that put the phone wire through the floorboard? This guy has he just laid his phone wire down for his house, and his house got struck by lightning. In the middle of the night, they hear this crashing noise in addition to the thunder. He goes out in the hallway, and there's this perfect break in the wood all the way down because the telephone wire straightened up from the electricity and shot through the bottom of the floorboards. Uh-huh. Yeah. Okay, in the back of these packets, there's 2 pages. One of them shows the chart 1 through 10. The next one shows the pick one options and stuff like that. This is also part of your homework. I forgot to put it on the sheet. Bring these sheets filled out next week. So what these do, this first one of the 2 where it's all the 1 through 10 numbers, Please be honest about them. These numbers go into a computer program, and we actually use this to help with grant money. And we also use it to make sure that our classes are at or exceeding the average. We actually hold our classes higher. Our average number for our classes need to be an 8 or higher. If any number goes below 8, we actually cut the course. So far, the ham radio class has not gotten anywhere near the 8, so we're happy about that. But there was a few classes we had that dropped down into the 7 and 6s, and we went ahead and cut the courses out. This way, we know how well you guys are taking the course. The next one is just strictly for us. This is so we know, how did you hear about the class? We know what advertising we're doing is working, what's not working, and where we need to put more advertising finances into. That's pretty much all that's for. Also, the distances help us out when we talk to individuals on where we're servicing. We have an updated map for anybody who comes from different areas. We can get an average distance of how far people are coming for the class. So bring those filled in next week, and your RF device for next week. Now, I want to jump ahead one more week just to get you guys prepared for this. The following week is week 5, which is our test only. So we have no teaching at all, but we will have a 1-hour review session beforehand. All 3 of us are going to be here, and you guys ask us as many questions as you want. This is for your time. Last class, everyone was kind of confident about it, and we just went ahead and ran through a bunch of different formulas and different questions and stuff from the book. But bring your questions to us on that day as well if you have something that you just don't get. Also, on the test, they ask. Yep. Yeah. Also, we have, and you'll see this in the book, set up for an FCC FRN number. At the end of the class next week, I'm going to walk you through how to get your FRN number. Our people that come to do our testing session, when you have your FRN number with you, it makes your process 10 times faster when you're going through the line. Also, when they submit your information, that FRN number is already registered. So if we get the information in time, you actually might be able to walk out of here on week 5 with your license, your call sign in hand as you walk out the door. So that's why they ask us to get the FRN number ahead of time for everybody. And we'll help walk you through that. You're going to Palmer Lake? No, Parker. They don't require the FRN number to begin with. They just can run with the Social Security number. Still get your FRN number beforehand. It makes things a lot easier when you're going through the line of the test. We'll help you get it. Yeah, it's super easy. Yep. You can if you want, or you can do it at home. Either way will work. If you don't have a computer access at home, let us know and we'll get you on one of ours and we can get you registered here on that day as well. Well, and then we can help you out with it here. Yeah, we can, and we'll do it at the end of class for you here. Nope. Well, you cannot test here. Yeah, here without an FRN. No. Yep. There's a whole bunch of different stuff that they do with, and because they're not our testing group, this is theirs, we have to follow their rules. And that's why we want to make sure that we get that. So before we end tonight, is there anything anyone wants to ask? I know it's late. We're ending on time tonight. Look at that. Last week you ended early. The week before that. No, you were early. Mm-hmm. If you see something like this, like the Apple TV remote with that little black line, this is a non-RF. That's the infrared light. It's behind this glass. So, all right, we got everything. We good? Thank you all for coming to day 3. We look forward to seeing you in our last class next week. We get to talk about space contacts and the best of all, safety.